Assalamu alaikum warahmatullahi ta'ala wa barakatuh. Ladies and gentlemen, welcome back to another live stream. Okay, well, let me just make sure to share the thing. Well, live stream, let's make sure everything's right. To copy the link, gonna post it around here. Let's go. Join my Discord server if you'd like to get notified every time I go live or I post a video. And also let's post it in the Zig server. Let's see. Where is it? Streams. There you go. Okay. Alright. Alrighty, well. Let's actually pop out the chat around here. There you go. Cool. Cool. Alright, so we're just gonna wait around 5 to 10 minutes just so interested people can join in. I always have this margin in my live streams. Just making sure if someone is interested, he doesn't miss out on anything. And yeah, pretty much. It's around 2 minutes already. And let's go. Let's go. Dut. Okay. Let's go. Alright. Let me pin this guy. Pin message. And let's go. Alright, so let's just wait a bit for anyone to catch up. And we'll start our new adventure. Okay. Stream looking great. Okay, so 5 minutes already up, so I think I'll basically start. Okay, let's go. So, alright. So we're going to start from scratch. We have done around 4 streams, basically trying to use Vulkan raw, without any bindings, without any helpers, without any dependencies. But today we're gonna actually start creating an actual application instead of just exploring the Vulkan API with Zig. Okay, of course we did learn a lot by trying to roll everything on our own, but it's not so maintainable. Okay, so let's go ahead and try this out. So we're gonna create a console right here. I'm gonna go to my document /zig. Okay, I have some projects here. Oopsies. Let's create a new project, mkdir. So what to call the project? Well, I guess let's call it Zig Vulkan Compute, I guess, or Vulkan Zig Compute. So creative name indeed. But let's go. I chose to limit our scope to only compute instead of graphics and windowing and stuff, just so we can get an opportunity to basically focus just on the Vulkan API instead of being bogged down and distracted by other craziness that is not cross-platform and other libraries, etc. So just a lot of things to keep track of at the same time. So I think it's probably a wise option to limit our scope to Vulkan Compute, and maybe even the first version of Vulkan, and the minimum of extensions, just to make sure we're not distracted by extra stuff. So anyway, all right, cool. Well, so we're actually inside the new folder of the project. So now I'm going to say zig init-exe. Let's go. Now code point, so we can launch code right here. Okay, great. Let's go to build.zig. All right, so I'd like to always add something to my build.zig, which is to basically make sure, I don't quite remember. Let me look into my other project that we have made earlier. So we're going to borrow a lot of code from it, although nothing really serious. So where is it? There you go, Vulkan Zig. Okay. So you could look out for the other streams if you're interested into seeing without using any binding or anything. You just Zig. Pretty much you could look up this project that we made earlier. But anyway, so I'd like to go to build.zig here. Okay, there we go. So I'm just gonna copy this guy, and of course I should do it after the exe, maybe somewhere around here. So allows Windows to build for release small. So if you don't say exe.strip equal to true in the release small build, then well, it wouldn't work. It would just error. So make sure to have this added to any one of your Zig projects, at least until this stream, until currently. And oh, I almost forgot about the chat. Okay, no need for this anymore. The stream looking great. Okay, nice, amazing. So now we gotta figure out how to actually set up Vulkan Zig binding, and of course we have it here. So Snektron Vulkan-Zig. I'm going to put the link in the chat. Let's go. Nice. And also here's my other project. Let me just send the link to. There you go. Nice. Okay. Vulkan binding generator for Zig. So I really advise you to read through all of this craziness through all this page, but anyway, we'll just try our best to make this work. So first of all, we have to let's see, const vacate gen is equal import vulkan-zig generator slash index.zig slash generator. You said, well, I think I have to basically copy the link right here, and I guess I'm going to go ahead and say I'm going to create a new directory called lib. There we go, inside of lib, and here I'm going to clone my thing. So but before that, honestly, I think I'm going to clone it as a sub module maybe. So let's first of all git init here. Let's go, and of course in the root directory, make sure you do that. Also, I'd like to change the branch name to master, because to main, because master is kind of like, I guess, deprecated, or at least subject to change. But anyway, git branch -m, and you call your branch whatever you want. In my case, it's going to be main. Cool. So I'm going to go back inside of that lib folder, and we're basically going to clone submodule. So git submodule add, and just paste in the link, and there you go, we got the submodule done. cd vulkan-zig, let's go. Okay, now let's try to figure out how to make this work. So it seems to have an index.zig, isn't it? An index.zig generator, I guess. Yeah, there is index.zig right there. Cool. So let's try that out, I guess. So we're going to get to our build stuff, and we're going to basically copy this guy, and let's try if this works or not. I honestly did have a really bad experience with Zig build system so far. Especially that there is no, well, not no, but almost like very poor documentation, especially for the build system. But yeah, hopefully this would work. So let's go, const add executable. Especially that Zig is constantly evolving currently. It's still not stable enough, but anyway. Create a step that generates vacate.zig stored in zig-cache from the provided Vulkan registry. So you basically create a step. There you go. Okay. So I'm not sure where I should put it, but I guess I'm going to put it after creating my exe stuff maybe. And then I would basically say this. Add the generated file as package to the final executable. Add module, Vulkan, let's go. Now, one thing that really tripped me off last time I tried this is the fact that I'm supposed to change this guy, this path right here. But I thought I would just copy this stuff and it would just work. I didn't really pay too much attention to that. I have to actually change this path. So now I have to figure out where vacate.xml in my system. Now it depends on how you install your Vulkan headers and craziness, stuff like that. Your Vulkan SDK, you're going to find that vacate.xml somewhere in your system. You could look up in the web on how to do that depending on your platform. In my case, since I'm on Linux, I can do something very, very simple. I could just search for it. So I could just say find / you could even search from the root directory, and you say -name, and then I'm going to look for vacate.xml, and I'm going to try to find where my thing is. Okay, so as you can see, I can see here that there is /usr/ let me actually zoom in a bit, so if there is some mobile users right here. Okay, I do remember there was some trick so you don't get this permission denied stuff, but anyway, we do not have time for that. I think you basically say I guess grep, I don't know, I don't remember well, but anyway, who cares. So anyway, so as you can see here, there's /usr/share/vulkan/registry/vk.xml. This is where it is in my system, so I'm just going to copy that path and I'm going to replace this one here, and there you go. The other stuff is from the provided Vulkan registry. Okay, cool. I don't know if I have to do something else, but let's try this out. Zig build run. Of course, make sure you are in the root directory. So no step named run for some reason. What? The following build command failed with exit code 1. What are you talking about? I'm actually in the wrong directory. Oh my god. I should give advice to myself now. Zig build run, okay. Well, enable to Lloyd index.zig file not found. And that's simple because we have to change the path to the path that we used, which is in my case I put it inside of a lib directory where basically I put my dependencies right there. So it's going to be lib/vulkan-zig/generator/index.zig. Let's try again, hopefully. Okay, expected two arguments found 3, and let's go. Now we're gonna fight with the build system. Oh man. So error expected 2 arguments found 3. Found 3. So this actually gives us generate step. Seems like it's only taken 2 arguments. Weird. Weird. Here we go again. Maybe let's try to remove this guy. Possibly. Let's see what's gonna happen. And there you go. Now expected 2 arguments found 3. What? Expected 2 arguments found 3. What? Expected 2 arguments found 3. Expected 2 arguments found 3. What 3 are you talking about? Did I actually save this file? This is super weird. Oh, Vulkan-generate error file not found. Yeah, I think maybe I have to generate something. So let's try to go inside of cd vulkan-zig, I guess, maybe. Oh, cd lib/vulkan-zig. Let's go. And maybe I have to generate something there. Vulkan binding can be generated from the Vulkan XML registry compile time with build by .zig. So I guess maybe I have to use the CLI interface. I don't know. Anyway, well, so if I do this, zig out, zig dash out /bin/vulkan-zig generator, path to vacate.xml. And I couldn't paste the path here that I got earlier. Oh man. Okay. That I get earlier. And I don't have it anymore, so let's find it again. So find copy. Let's go. Okay. And let's actually replace this path to vacate.xml with that path of the registry vacate.xml. And then here output path to vacate.zig. I guess I'm just gonna call it well. But no, this is not. Oh my god. I never really understand the Zig build system. It's stupid. I don't know. Vacate.xml. Okay, hold on a second. Go back. File not found. Okay, where that happened. It's not even giving me where that happened. That's stupid. Gen get module. Initialize a Vulkan generation step for builder. Spec path is the path to vacate.xml relative to the project root. What? The generation button will be placed at out path, which is but why it's relative to the project root? That's stupid. Okay, hold on a second. What if I put there the path to the XML thing? Okay, let's replace this with this guy. And this seems to work, I guess, maybe. So I guess it's changed. You no longer give it this vacate.zig stupid thing. So you just do this, seems like. Alright, add module, Vulkan. Okay, so what's next? What we do next? This is honestly why I hate to kind of use Zig libraries, just because I always have problems with the build system and documentation, etc. Anyway, well, let's see if this works by any chance. Now, how do you actually import that stuff? I guess you do this. So let's try it out. Const vacate equal to import Vulkan, seems fine. So now if I say vacate dot, And yeah, I don't have any stuff. Anyway, let's see. So const base dispatch, let's try this one. What? I don't know why it's run like 3 times there, but anyway. So that seems, I guess, to work, maybe. Let's remove this test. Let's remove this boilerplate stuff, anyway. And let's try to do this. Let's try to use this for something. I guess let's try to print maybe something right there. Okay, let's see, say vk maybe dot, for example. Okay, this is so bad because you do not have any stupid highlighting. That's why I also hate Zig build system again. Well, not the build system itself now, but the ZLS. But anyway. Right, well. Extension info. But I have a generated binding here. I have it in, what can I say? In here, okay. I generated it earlier. So let's just open that one up. Then we could use it kind of like that. All right, amazing. So now vk.zig, let's look for extension info. Real quick, let's look for something like, for example, this guy, although I just need to verify that this is actually working. Yeah, let's do this. Yeah, our C ZLS doesn't run custom build steps at the moment because it's kind of not the safest things to do. Welcome Jeremiah to the stream. Yeah, let's make sure this at least works. Let's make sure that this is a string. And what happened there? Okay, so it works. All right, fine, at least it works. So this is nice, but for now I guess there could be a little thing that we're going to do here as a workaround so we can get a bit of highlighting and auto completion. Is basically I'm going to take this generated vk.zig, which by the way you could generate it by basically going to the if you go to the library, right, generator, let me see, hold on a second. You go to inside, I'm going to go inside lib and vulkan-zig. I just figured out that I actually should tell you how to generate that file. Although you probably can find it in somewhere hidden in the zig cache. But zig cache is always very hard to find stuff in. Although I may be able to use the find command. I mean, if I say find dash name, well, dot and dash name vk.xml. Sorry, not XML, but vk.zig, I guess. Okay, so as you can see, it's inside zig cache /o/ this crazy hash right here /vk.zig. But of course, if you are like, it's hard to find, okay? So here's how you do it the right way, I guess, or the simple way. Anyway, you're going to go to vulkan-zig to lib. I'm going to go inside lib. I'm going to go inside vulkan-zig. All right, and if you go back to the page right here, and I always forget to not hide the chat. Okay. All right. If you go to CLI interface, okay, so you basically have to use this guy, this command right here. Right. Zig dash out slash bin slash Vulkan dash zig dash generator. Although I think you may need to actually first of all zig build run in that directory. Hold on a second. I should probably zig build run in this directory first. Maybe. Actually zig build, not zig build run, just zig build, right? And then it would generate the generator for you, etc. Right, and it would also generate for you an example. Let me show you. Dolphin. Okay, if you go to zig out, as you can see in bin, there is two things. There's a triangle binary and the generator binary. Now, if you click on that triangle, it's basically a demo that you can make sure or verify that the application would run on your system and you have Vulkan driver, etc. all good, you know, all good to go. So as you can see, it runs, it works fine. So this is the triangle. Okay. But it's very unresponsive for some reason. Is it back? Is the stream back? Hopefully it recovered. Let me know, guys. Is the stream back? I run that executable, it just I don't know, it's not, I think it's not very well made. Sorry for a second there, yeah. Because the stream like just stopped like completely because of FmpEg taking too long to encode the thing, because I'm using the GPU to encode here in the live stream. And all of this because I run that Vulkan triangle. I don't know, maybe they have missed some detail there in creating that example. But anyway. So, where should I go from here? Triangle 2 OP. Yeah, man. That is crazy. Well, alright, let me just exit out of it. I think the best option is probably to just say Control C on where you have run that thing to make sure it just completely exits, I guess. But anyway, let's go back to where we were. Okay, so if you go back to zig out, there's also another binary called generator. Now this generator is inside of bin, inside of zig out. That's why while you are inside of the libraries repo, you have to say zig dash out slash bin slash generator, right? And then you have to basically give it 2 arguments, I believe. I mean, if we go back, let's see. There you go. So you have to basically give it the path to vk.xml, which I've told you on how you can find it in your system, hopefully, at least in Linux. Okay, output slash path. In Windows, I think you probably have to find your Vulkan SDK folder, and then you probably can find it there, vk.xml. But anyway, and here output path to vk.zig. Okay, so path to vk.xml. Path. All right, so where did I put my path? I think I've lost it again, maybe. Actually, hold on a second. Maybe I could look out for it before. Hold on. Where is it? Okay, I have to find it again. Oh my god. Let's go. Oh, I think I just remembered how you can do this actually, by the way, to actually remove this permission denied and all these errors. I think if I remember well, you say 2 and then you do this guy. Let me zoom in a bit here. So you say find slash dash name vk.xml 2 in that thing. And then I guess you say slash div slash null if I remember. Yeah, exactly. So what I'm doing here, I'm basically directing the error, the std error stream to slash div slash null, which is basically a virtual device in Linux where you could basically redirect anything to it. It's a file, which anything you redirect to it, it just goes to the void. It's like a black hole. Because if you don't know, in Linux, everything is a file. Even devices are files. But anyway. So here's the path. Let's copy this guy. And after that, you basically pick any path you want to where you want it to generate the thing. So I'm just going to say, I guess, Vulkan vk.zig. And there you go. As you can see, it generated that vk.zig. Now, as a workaround, instead of doing this for now, just for the sake of autocomplete and highlighting, etc., I'm just going to say, instead of using the build system, I'm just going to say import and lib / vulkan-zig. It's very unfortunate that ZLS is still not so good, but anyway, that's life. Vulkan-zig / vk.zig. Okay. All right, let's see if this works. Oops, what I'm done. Okay, zig build run. Oh, let me go back to my root directory. And let's say zig build run enabled to file not found. Let me make sure I'm doing this right. Where is it? vk.zig lib / vulkan-zig / vk.zig. So what's the problem? That's crazy. Copy relative path, I guess. I mean, it's the exact same thing, so what's the problem? Enable to load. Oh, because they have to be in src. Oh yeah, that's problem. All right, gotcha. Oh man. Okay. So I'm gonna say lib / vulkan-zig again. I'm gonna say zig-out /bin / generator, yes, generator, and then I'm going to basically say, I'm going to give it that path again. There you go. Going to copy, paste there. Oops, it didn't copy it for some reason. That's stupid. Control-Shift-C, Control-Shift-V. Let's go, and then I'm going to tell it to put it inside of src. So src / vk.zig. And there you go. Nice. So I'm just going to put this into a script. So you only have to run that script. You don't have to go crazy with this. So new file, generate vk. And I'm going to say shebang, right? And /bin /sh. And I'm going to say, let's see, I'm just going to paste this command that I've used personally. So let's go. And of course, before that, you have to make sure to zig, I think zig build run. So let me see, zig build run. And I have to somehow, let's see if this would work or not. / maybe. Well, lib, I guess, / vulkan-zig. Okay, without the run here there. Zig build. No step named. Okay, well, it doesn't work that way. But can we maybe... how do I actually build another directory? That's crazy. Okay, let me try to say maybe after, or actually before it though. So I'm going to say cd lib / vulkan-zig. Man, this is crazy. Anyway, and then I'm basically going to say, I do remember there is a way in sh to actually push a path, if I remember. At least it's there in Windows, I believe. Yeah, push and pop, something like that. Bash push D. I wonder, yeah, pushed. But this is bash. I'm not sure if it works on sh when push D command is used without any driven path. Let me see if this works actually. Push D. No other directory. So it's there, I think. Okay, so I guess maybe I'm gonna say instead of cd, maybe push D. Maybe. Let's try this out, I guess. There you go. lib/vulkan.zig, and when you say pop, it's not called pop. I guess maybe it's called popd or something. What is it called? popd. Yeah, that's how it works. Okay, so I'm going to push that path and then I'm going to pop it after doing zig build run, I guess. Well, just zig build, I guess. So okay, cool. Now Vulkan zig compute. Okay, let's try this out, I guess. But of course, chmod +x to give myself execute permission. I'm going to do this. Okay, cool. Now I could basically /generate vk and enable to Lloyd src for some reason. src/lib. What? Enable to Lloyd src/lib. What are you talking about? Well, let us try ourselves, I guess. Let's see. Why I have this, by the way? Maybe try it again. Okay, generate vig seems to be fine. Now, if I remove that vk.zig there, where is it? Here you go. Let's remove it and let's see if this script works now. Yeah, it works. Okay, so you don't have to go through all this pain. You're just gonna say /generate vk and you're gonna find it here, as long as you have Linux, of course. Okay, well, that was crazy. But right now, at least, right now I could just say, instead of this for now, as a workaround, so I'm just gonna say that workaround for autocomplete. And okay, for autocomplete anyway, or for anyway, never mind. So hopefully this now works out. So if I say vk dot, okay, as you can see right now I have some of the autocomplete and stuff, which is nice, although not perfect, still not perfect, but there you go. And now if I zig build run, there you go, amazing. As you can see, it works, lovely. Okay, well, now finally we could work on the actual thing instead of fighting with zig build system. Okay, crazy stuff. Anyway, so Vulkan works kind of in a weird way, because basically, first of all, so there is a loader. I mean, let me actually give you a good article to actually, there you go, this one, to actually read it, okay, to understand what's going on here, because you probably won't. Okay, so I'm going to send you this link right here. Okay, so make sure to read through all of this so you can understand how the Vulkan loader works and how you're supposed to work with it for maximum performance. And basically this zig binding is actually making sure to go with that guidelines, okay, to make sure we have the maximum performance. So that means we have to basically load the loader. Well, honestly, let me try to give you a little glimpse of how that works. So here's our application, okay? Now you have a loader. It could be called vulkan-1.dll if you are on Windows. It could be called libvulkan.dlib or something like that, depending on your platform. Then you basically have to dynamically load that, or you could statically load it, but that's very not good, because you could fall into all sorts of problems if you statically link the Vulkan loader, okay, that I'm not going to go into right now. But anyway, we have to basically dynamically load the Vulkan library or the Vulkan loader, And when you call some Vulkan function through the Vulkan loader, you have to first of all go through the loader trampoline. Then you have to go through all the layers that you have enabled. If you have no layer, if you didn't enable any layers, then that means it will basically go right ahead from loader to the loader terminator. And then that loader terminator will redirect you to the right driver in your system, depending on the GPU you're working with, okay? So if you have selected the device of Intel, for example, you know, or you have like the integrated GPU, or you selected the NVIDIA GPU or whatever, depending on that, it would redirect you to the right driver, okay? That's the job of the loader, okay? Cool. Now, after you use vkget instance proc address, I believe, this guy right here to load your functions, you would remove one indirection from your call stack, I guess, which is the loader terminator. Right now, you only go through the loader trampoline, the layers, and then you go directly to the driver instead of needing a loader terminator that redirects you to the right driver. And then afterwards, I think when you use vkget device proc addr, after you have selected the device, you will basically use this to load the Vulkan driver's function pointers directly. Why? So we can go from the Vulkan application. When you call a Vulkan function, it will call directly into the driver instead of having, because if you don't do all of this, if you just use Vulkan like normal, like any library you're used to, what's going to happen is that every time you call a Vulkan function, you have to go through all this stuff, okay? You have to go through all this craziness. But when you do this, use this vkget instance proc addr and vkget device proc addr, you will, if you have no layers enabled, which you should not have enabled if you are on release build, but of course those layers are very useful for like debugging, etc. But in your release build, you will basically remove all layers. You won't enable any layers. And as you'll see soon, that I'm not going to use layers at all. I'm actually going to use them using another application that I'm about to show you. But anyway, basically, a Vulkan application will call directly into the driver. So we have no overhead whatsoever. We're directly calling to the driver. So we have the maximum performance possible. And if you come into Vulkan, you probably want the best maximum performance possible. Otherwise, go back to your OpenGL or maybe WGPU or something. Anyways, so this is what we're going to do. And that's why in this binding, this zig binding, of course, you have to do all of this manually if you don't use this binding or, stuff like that. But anyway, if you're using C, then you could use the Vulk meta loader. This one would do the job for you. It would load Vulkan dynamically and it would do all that stuff for you. You just have to call Vulk initialize at the start and then Vulk load instance to load your instance, and you'll optimize the device calls with Vulk load device, Vulk, etc. Stuff like this, okay? So you would use this library, which a lot of people do. But in our case, this zig binding already manages that for us. And in fact, Snektron, which is the author of this binding, it seems like to me is pretty. He knows exactly what he's doing so far, and that's very rare to see in the Vulkan ecosystem, like the Zig ecosystem. Sorry, nowadays. But anyway, okay, I wanted to talk about the wrappers. So where's the wrappers? Okay, so as you can see, you need a base dispatch wrapper, so a base wrapper, and then you're going to need an instance wrapper, which he didn't mention here, I guess. But basically, you need 3 wrappers. You need the base wrapper, the instance wrapper, and the device wrapper. The base wrapper would basically, you would use it to load functions that are not linked to any particular instance. Like, for example, to create an instance in the first place, you do not have an instance. So you would use some functions that aren't related to any instance, that doesn't really require any instance. So for example, to create an instance, you need this function create instance, which you would get by using this base wrapper. After that, you would get, for example, destroy instance, which works on an instance. You would get it using an instance wrapper, which we're about to see. And after that, you're done with the wrapper and stuff. And after you created the device, then you would basically use another thing called a device wrapper. But don't worry, I'm going to show all of this right now. So here we have a base dispatch, and we have .create instance. But before we go through this, first of all, this will basically just help us to get the definitions of Vulkan right, etc. But we have to actually call something. So vkb, so B stands for base dispatch, and vk stands for Vulkan, is equal to base dispatch, which we have created here, the thing that we have created here by the help of this base wrapper kind of macro thing, although there's no macros in Zig, but anyway. So Lloyd, so there is two options here. There's Lloyd and there's Lloyd no fail. So Lloyd, it would make sure to give you any error, an error if something happens wrong. For example, it didn't find a function in the driver or in the loader, sorry, or something like that. It would fail and it would give you an error. But you could also use Lloyd no fail, which would use indefined behavior. So if there is a function that is not there, it wouldn't give you an error. It would just God knows what's gonna happen at that point. You're basically in defined behavior land. So probably you would like to use Lloyd for your sanity. So that's just a recommendation. Okay. And here we're going to pass in here we have to give it a loader. And the loader would be vk get instance proc addr. Now, if you're, for example, using g of w, there's vk get proc addr. Let me show you. So, for example, if you're using g of w, you would use get proc add. There you go. This guy right here. This g of w get proc address. You would pass this function, okay, into as a loader, okay. Why? This function, you give it any name and then it would load that function with that name from the library. There you go. This function does not, actually this function does not apply to Vulkan. If you're rendering Vulkan C g of w get instance. Oh, there you go. Sorry. So this is the one. Okay. So it's called g of w get instance proc address. This is the one that you have to pass as a loader if you're using g of w, which you basically give an instance in. When you don't have an instance, for example, you want to load create instance, then you would use null here, which is valid, of course. Const char proc name, you would say vk create instance here, as you can see here. But this would be done for us by the base dispatch stuff, by the binding. Okay, so, but I'd like to not use any g of w, any SDL, nothing. I'm just going to use Zig to do that. And luckily, I already have done that before when I was exploring how to do everything myself using Zig and Vulkan. So if you go back to my, this repo right here, I'm not sure if I linked to it. I guess I did, yeah. Okay, so if you go to src main.zig, okay, there you go, all this craziness right here. So first of all, I would get this library names right here. So I would create a Vulkan. Okay, let's just create a Vulkan loader struct right now. So const Vulkan loader is equal to a struct. So we encapsulate all that stuff for now. For now, I'm just going to comment that out. Okay. Now we're going to have an if init function, which would basically give an error or Vulkan loader, and of course we're going to have a dinit function. Okay. All right. Cool. Now in the init function, I would. Oh, by the way, let me first of all grab this guy. I'm going to put it as a constant. So this will be done in comp time, in compile time, library names. And here I need the built-in. So const built-in is equal to import built-in. Okay, let's go. So here at comp time, because here we have a constant, it would switch on the built-in.os.tag and it would see what platform we're compiling into. If we're compiling into Windows, this would basically resolve to, this constant would basically resolve to this guy, okay? Kind of, right? If you're compiling to iOS or macOS or tvOS or watchOS, etc., we're gonna use this guys, okay? And if we're otherwise, for example, Linux, then we're gonna use these names, okay? So depending on the platform, we're going to try to load one of these names. So for example, if libvulkan.dlib didn't work, we're going to try to load using this name instead. If that didn't work, then we're going to try this one. If none of them works, well, we're done. We cannot load it, so we're just going to error. And by the way, I got these names of the dynamic libraries. I got them from Vulkan. So if you go to look for the Vulkan, hold on a second, Vulkan MetaLoader, if you look into the source code of it, let's go, vulk.c, I believe. And if you look for .dll, for example, you're gonna find that here we have a C macro. So basically we're saying if defined Win32, which means Windows, we're going to use the Lloyd library A, which is a system like Win32 function call, and we're going to try to Lloyd vulkan-1.dll. So basically I got the name here. Otherwise it will return vk error initialization failed. Okay. Otherwise, if we are on Apple, we're going to try to use dlopen, which is basically a function in libc. And we're going to try this name. If it doesn't work, then we're going to try this one. If that doesn't work too, then we're going to use this one. Otherwise, if none of them works, we're going to return a vk error initialization failed. And the same thing with anything else. So this is where I got the names basically of the libraries. And so this is what we're going to do now. Okay, so now in the init function, we're going to go through all the libraries. So for library names, library name, and notice that I actually made library names a constant as to make sure this is executed in compile time. This is resolved in compile time. Okay, in used capture, so here I'm going to try to use std.dylib. You could also use, if you're linking to libc, which we're actually required to do that currently, unfortunately, because in fact, first of all, we're working with a C library, so I'm not sure if that really needs that. Otherwise, there is currently a bug in dynlib. If you're not linking with libc, it will fail, too simply because internally it's just using std.c.dlopen, because basically there is a bug. I don't remember exactly, but it's something like, hold on, zig dynlib, and let me see if I can find it here. Fails to open. Okay, let's see this one, I guess. All right, there you go. So without that, first of all, you would need to tell it the full path of the library. So you won't just say vulkan-1.dll, you have to give it the full path of the library. And the second thing, if you actually have done that, it would give you another error called the elf hash table not found. And if you bring it down a bit here, you would find another one here called, okay, so here's an issue. It seems to be closed somehow, but anyway. So it seems currently std.dynlib without the C library. It's, of course, they're implementing it themselves. So they're using something called dt hash, which is the legacy way of doing it. But now there is dt gnu hash, which is basically used by a lot of libraries nowadays, like including Vulkan. That's why it fails to load it. So they need to basically implement dt gnu hash for it to work properly without libc. But anyway, so for that we have to make sure to link to libc. Okay, where is it? Link libc, add module. exe.link libc. By the way, the order doesn't matter much of the time because this is not imperative, I guess it is called, but basically it's, yeah, looks imperative. Note that its job is to declaratively construct a built graph. So just a graph that will be executed by an external runner. That's why order doesn't really matter that much. Okay, so just make sure to link libc. By the way, if you want to statically link Vulkan, which I don't recommend to do, you would say link system library, sorry, and then you would say Vulkan. But I don't recommend to do this. If you do this, you wouldn't need to load Vulkan dynamically and all this craziness. But I don't recommend to do it for performance reasons and also for compatibility reasons. Okay, so now let's just use dynlib, and you would say the open, and you would try to use that library name to open it. Okay, const. Well, I'm gonna actually go with the var library is equal to that, and then the fur library dot dinit. Well, actually not here. Yeah, it's fine here. Although I would always, as a good, what can I say? As a good practice, always try to use defer, and you would say library dot, because in fact I missed it in my other repo that I've been experimenting with and exploring Vulkan with. But anyway, defer library dot close. Okay, always do this. Always use defer. So if any error happens anyway, like if you add some code right here that could error, this would happen if the function errors. Okay. In the init function though, we would say, well, we need first of all a field here. Let's call it, I guess, handle. I'd like to call it handle anyway, and I'd like to, well, std.dynlib basically. Okay, and then you would say, of course, this dinit would take self, and I always like to do this const self, and notice that in Zig, the style guide basically says that you have to use this kind of naming scheme for types, and otherwise using this kind of naming. Anyway, const self is equal to this. This would basically resolve to Vulkan loader in this case because it's inside Vulkan loader struct. Anyway, so for example, if you change this name right here, it wouldn't matter because we're going to be using self. All right, fine. So here we're going to say self.handle.close. As basic as that. All right. Now this could fail, of course. So what we're going to do, well, if, I'm going to say if this actually was successful, then we're going to defer, do this. Else, if there's some kind of error, I'm just going to ignore it for now. And yeah, and if we wasn't successful on any one of these guys, then we're basically going to return error dot or maybe fail to initialize or something like that. Hold on. Hold on, what the failed to initialize. Error initialization failed. Okay, I'll just use this guy just like how Vulkan does it anyway. Why not? Or honestly, no need, never mind. Let's just do it the normal Zig way. So return error dot initialization failed. Let's go. So defer use of undeclared identifier library. Yep, so const library here, well, var, sorry. Var library is equal to cd.dynlib open. No, what I'm doing here. You'd have to capture the thing, okay? Here would give you the library, basically, the loaded library. And then you would just basically do this. Otherwise, you would return finally. And this point to basically defer from the return type of the function. So you could also do it this way, but since I could basically tell it to infer it, sorry. So return that, and then I would say dot handle is equal to library. Let's go. All right, nice. I think this should work, hopefully. And now what I would do, const vkb base dispatch.loid. But of course, first of all, I need to get the loader here. So const loader is equal to Vulkan loader dot init. Let's go. And I would, I guess, try it out because it could fail. And then I would pass here the loader, but not the loader itself. I should pass in, as I said, the function pointer get instance proc addr, right? This guy. So how we're going to do that? Well, I'm going to add another member here called get instance proc addr, and that would be, let's see. Oh yeah, sorry. Vk get instance proc addr pfn get instance proc addr. Notice that we do not need to see vk because the binding does that for us. It just removes that initial kind of name of vk. Yeah, and instead of pfn like this in Zig, you just have this pfn like this. All right. So this is the type basically. And by the way, in C you would have an optional right here, because like in C all pointers can be optional, but here using the binding you don't have that. If you do though, if you're using that C stuff, then you would have to say std.meta.child, and you would say this. But in our case, since the binding is doing that stuff for us, we don't need to do that. Okay, and of course we have to initialize that. And how we would do that? Well, too simply by saying library.lookup, and here you give it some type, which is in this case would be vk.pfn get instance proc addr, and of course you would tell it the name of the symbol in that dynamic library, which is, it's going to be vk. Now here you would use the actual name in the library, which is basically vk get instance proc addr. All right, cool stuff. I wonder if this name actually in the binding, so we could just refer to it. Let me just have a look real quick. Okay, it's right there. Although I'm not sure how would I get it. But anyway, it's fine. It's fine. Anyway, never mind. Let's just keep it like this. Okay, there you go. By the way, there may be some way of loading the library without having to do all this stuff that I do not know of. But so far, from what I've seen in vk.zig, you have to take care of loading stuff yourself. So anyway. So this is pretty much it. But of course, this lookup function would give you an optional. It would give you the symbol if it succeeded, if it finds it. If not, it would basically give you null. So you could do this, but then it's kind of like base dispatch.load no fail, like this one, load no fail. If you do it this way, because this basically says or else undefined, I believe. So yeah. But the better way, just to make sure that if there is any error, we would know about that, so we can keep our hair intact. We would say or else return, let's say we're going to return some error, like the initialization failed anyway. Okay, there you go. Otherwise, if it's null, we're going to return error.initialization failed. If not, if that's fine, then we're just going to return this stuff. Okay, cool. So this should hopefully work. And of course, the fur loader.dinit. And yeah, right now we do need this error defer. Why we need it? Now I have an example of why we need it in this case. So if this lookup function returns an error, we would make this error deferrer would make sure to close that the library before we return that error, you know. Otherwise, if we do not return an error, this wouldn't work because, well, we're going to use dinit to do that then when we're done with it. So yeah. Okay, cool. So defer loader.dinit base dispatch load loader.gameinstance proc addr. Okay, amazing. Const vkb. Let's try this out. Let's make sure there's no errors there, hopefully. Okay, sure. There's an error, but it's probably something very sweet, very cute. Okay, expected type. So the thing is, when you have a capture, it would basically, I believe, here, this library capture, or basically function parameters, are always constant, so you cannot change them. In this case, lookup, I believe it's trying to change it or something. I don't know exactly what's trying to change it, but anyway. How you would fix this, you could basically declare another variable inside. Let's call it, for example, handle, and then you would refer to that that parameter or whatever it is. In this case, it's a capture, and you would say this var handle is equal to library, for example, and I could just use that one instead now. Okay. Oh yeah, I have to use it here. Okay. What's the problem here? So control flow reaches end of body here. Oh yeah, sorry, not here. I didn't meant to put it here. I meant to put it here. Okay. So after we're done basically of looping through all the library names, if we failed on all of them, then we're going to return that error. So consider using try and catch. Okay. Well, this could fail basically. So you would say try base dispatch.load. And I believe maybe this loader have to be variable. No? Oh yeah, sorry. Basically this self should be a pointer since we're using close, which is trying to change that. And I guess maybe we also need that variable right there. And finally, it works. Finally, after all this craziness. Okay, so as you can see right now, it compiles fine. So now we could actually use that stuff that we have loaded. So every time you need a new function in the base wrapper, you would add it here. Okay, so for example here I said dot create instance equal to true, and it would basically do its job to generate for you the stuff that is related to it, like errors, etc. Okay, cool. Now I could basically say vkb dot create instance. Now we actually enter the meat of the Vulkan API. So here you would need to pass create info, which I could basically do like this. You would say the address, and then you could say this. And for the allocator for now, I'm gonna go with null allocation callbacks. So null for now. Okay. Now here you need to pass the create info stuff. And how you would know this about this stuff, you would look up in the internet, in the browser. Okay. So vk create instance. But let me show you how you would find it. vk create instance. Use whatever search engine you'd like, and just look for the registry website, and you would find a lot of stuff about it, like the parameters, the description, the valid usage, the return codes too. But yeah, stuff like this. So, and also you would find in C also you'd find some stuff that is related to it. For example, in this case we need to know more about vk instance create info. what parameters we'd like there. Okay, so there is vk structure type, which we'd have to pass to all structs to tell it which struct it is. But in our case, the binding is doing that for us automatically. The binding automatically makes sure to make the default values of all these guys, of all the other parameters, to 0 or null, depending on if it's a pointer or if it's a number, etc. So for example, pnex by default it would be null, flags by default it would be 0, p application info null. You got the point, okay? And then you could basically override whatever you would like. Now there is p application info, which we're gonna come to in a second. There's flags, there's enable layer count, and in pp enable layer names. This is where you actually can enable layers, but I'm not going to use layers through my application. Why? Because there is a much simpler way and much better way of doing this by using vk-config. Now if you actually like for example, for me, I'm using the package manager, and if I look into groups, I can find the Vulkan stuff. Where is it? The Vulkan group, or sorry, Vulkan dev, I think. Yeah, there we go. Vulkan-devel development, you know. So anyway, so there's all these packages like SpareV tools, Vulkan headers, Vulkan extra layers, Vulkan-tools. So I installed this Vulkan-extra layers. By the way, if you're on Windows or some other platforms, you could just basically go ahead, install the Vulkan SDK, it would do all this stuff for you. If you have a package manager like me, for example, I'm in Arch Linux, exactly Manjaro, I needed to install all this stuff, especially like Vulkan extra layers, which would give me all the other layers like vk layer API dump, vk layer monitor, screenshot, API dump, monitor, screenshot, etc. And there's the Vulkan headers right here, the validation layers. This is also needed. This would give you the validation layers, and the extra tools, which would give you vk-via and vk-config. Okay, so do you need this for vk-config? So if I say vk-config, it would launch this application for you that is coming, of course, from the SDK. And here you can basically choose to enable any layer you want, and it would apply on any Vulkan application you run without you having to actually go ahead and change the code to do it. So for example, let's say I'd like validation layer. I would just click on it, make sure that overriding layers by the Vulkan configurator is on, and I would basically launch another terminal. I would say zig build run, and it works, but there's no validation layer messages, seems like, at least not yet. And I could also choose to see the API dump. I wonder, so we're not calling any stuff yet, because right now we're just saying, I guess. So yeah, I didn't save, seems like, right? No, okay, so error is ignored. So the binding, like automatically, it basically handle converting Vulkan error codes to actual Zig error codes, as you can see here. Create instance error. So I could just say try, and value of vk instance is ignored. So here it would give me the instance. All right, and there you go. So since I have this API dump layer is on, as you can see, I can see all the API functions that are being called, and I can see the result. In this case, it's vk success, which means it's successful. And also I could see all the parameters, what I passed to it. For example, here, as you can see, vk structure type, it passed vk structure type instance create info, and the other stuff is null, 0, null, 0, null, 0, 0, because I didn't basically allocation callbacks null, vk instance is an address, because I didn't override anything here. Now so if you are on macOS with Vulkan is kind of complicated situation, because macOS is trying to stick with its own ways of doing stuff, like the Metal graphics API. They have its own graphics API. So to support it, you have to make sure to add some flags. because the molten vk that we use to kind of as a compatibility layer between Vulkan and metal, molten vk, there you go. So this is not considered to be 100% Vulkan conformant. So to be able to enumerate its physical device, enumerate it into your thing, you have to make sure to add a flag and an extension, which we're going to do right now to make sure our application is fully cross-platform. So at least with Mac OS and Apple products in general. So how we're going to do that? Well, we need the, first of all, let's enable extension count is equal to, as you can see, the binding also changes the names of the fields, as you can see. So this, this becomes this. So enable extension count, I'm just going to say extensions.len. And then dot pp enabled extension names, there you go. By the way, pp basically means a pointer to a pointer, basically double pointer, because we have an array of strings, and in C, a string is basically a pointer to the first character in that string, and the length is determined by the null byte in that string. So it keeps on reading that string, for example, until it reaches 0 byte, the byte 0, and it stops. It knows that that string is, the end of that string is there. Anyway, pp enable extension names, we would say extensions.ptr. Now, of course, I still didn't create this extensions slice, so let's create it here. Const extensions is equal to, okay, let's see. So I'm going to create a slice here. So const slice, so u8, const u8, okay. And then you would say this guy address dot to infer the type, and then here you could give it the extensions that you'd like to enable, and it would of course take the length of that slice, it would put it in this guy, and it would take the pointer to that slice, and it would put it inside of here. By the way, slices are called also called fat pointers, because they basically contain a pointer, which is basically the location memory, but also a length, which tells you the length that you're pointing to. But anyway, so extensions, here we would say vk.extensionInfo. So inside of this struct, because of the binding, is basically putting all the generated names inside of here of the extensions, and you could use them. And thanks to Zig, by the way, all of the stuff that is generated in that Zig file or whatever that you use in the standard library, etc., anything that you don't use, you don't pay for. It basically doesn't even get compiled, and that's why sometimes you don't see errors until you use something, because it doesn't even get compiled until you need it, or until you use it, should I say, in your application. But anyway, in my case, I'm going to go with the enumerate portability extension. So it's called KHR portability enumeration. And not stop there. So there's two fields inside of that struct. There is the name of the extension, and there is the version. So we need the name, and notice that it's actually a slice to a const u8. And it's, of course, stops at the null byte. That's why there is this 0 thing right here. Okay, dot name. And if you actually hold Control and click on it, you can notice that it's like this. And yeah, cool. So instead of specifying the name yourself, which would be error prone, you just do it this way, which is much better. Okay, cool. So hopefully this is it for the extensions, at least. Let's see, Zig build run, and expected type const u8. I wonder if I really need this guy. Hold on a second. Type const here does not support array initialization. Okay, I think maybe I need to do it this way. Sorry, maybe this way. Let's see. No, that's not how it works. Oh, I guess I remember now. Hold on. I just missed something. Which, let's go back a second there. Okay, there you go. So you need to add this guy. Since we're working with C strings, you need to add this guy. Don't forget it. So you just add this, and hopefully it should work. And there you go. As you can see, if you enable the API dump, we can see right now that it's surely passing 1 to the extension count and the extension names, VKKHR portability enumeration. And if you, of course, make sure to go with the validation, and if there's any problem with how you use Vulkan, it may tell you through the validation layers. And right now it doesn't tell us anything, so all good. Okay. Now we have enabled the extension count, but of course it doesn't stop here to actually support Mac OS. You have to also add a flag. So if you say .flags is equal to, and I don't really remember how you get the flags. vk.flags, I guess. Sorry, .instance, I guess instance create flags. There you go, dot. And oh, you actually. So bit flags in using this binding, it's kind of doing it in a cool way. So it's basically a struct, right? And of course, by default, they're all false. All the options are false, but you're responsible to actually enable any option that you'd like. So in our case, instant create flags currently only have one flag anyway, which is enumerate portability bit KHR. So you have to make sure to add that. So .enumerate portability bit KHR is equal to true. And finally, right now, hopefully I don't have a Mac OS to test this, but hopefully this would work on Mac OS. Okay, pretty cool stuff. All right. If you want Vulkan, this is Vulkan. Okay. All right, amazing stuff. So yeah, now just make sure that you actually go ahead and destroy the instance. So how you would do that? Well, now before we are able to do this, we have to go to the next level of the wrapper. So now we have to create another dispatch. It's going to be called instance dispatch, because right now we got an instance. Right now we have the instance that we're working with. We have created one. Now we have to use the next layer, instance dispatch, vk.instance wrapper. And here you give it a comp time commands. And if you'd like to see never mind anyway. So this is the generated stuff anyway, never mind. So here you could pass in the functions that you'd like to load. So in my case, I'm going to load destroy instance for now. I'm going to say equal to true. And the also nice thing about this is that you only load the functions that you're going to use in Vulkan, instead of having everything, all the functions mapped to your executable memory. So let's go. Nice. And also you get, with dynamic stuff, you get to choose what you want to do when you have failed to find, let's say, for example, a function pointer, a particular function, or you have even failed to find the Vulkan library. For example, you could ask the user to basically go ahead and download the Vulkan SDK, for example, or to update their drivers, etc. But yeah, that is something to know. Okay, so after adding this, right now what we could do, we have to get the const vki. Vki stands for Vulkan instance, basically, just like vkb stands for Vulkan base. Okay, so vki try, instead of base dispatch, we're going to say instance dispatch dot load, and here you would give it the instance that you have just created, which is this guy, and then you would give it the loader. The loader in this case would be, well, Pretty much the same thing you used here, I believe, if I'm not mistaken. So get instance proc addr. That's the vki. Okay. And after that, now we could say vki dot, well, defer vki dot destroy instance. And then we could pass it in the instance. And then the allocator. And for now, I'm just going to go with null for the allocator. Or should I say allocation callbacks anyway. And there you go. Now if we zig build run, and if I enable the layer API dump, and as you can see, I can see that it actually have gone ahead and successfully called vacate destroy instance. Yeah, I've gave it the vacate instance, and there you go, done. That's very nice. Cool. Now the problem that I don't know if you have noticed this or not, but there is a subtle problem here that I wonder if anyone have paid attention to, which is the fact that it could fail. It could fail that we wasn't able to somehow load the instance dispatch because we have a try here, and at that point the instance would be leaked. You wouldn't destroy the instance. So like, if you don't mind about that, then fine, you could just continue with your adventure. But in my case, I'd like to make sure everything is fine. So what you could do in that case, you could load the destroy instance in both, maybe. Let me try. I never really tried it, honestly. But let me see what's gonna happen if I did this real quick. No field name destroy instance. Well, that's interesting. I cannot do that. I'm not honestly sure how you would do it using the binding, but basically you could just, if you fail to get the instance dispatch, you could just use the base dispatch anyways. You could just use the loiter, although there is the overhead, but you could just use the loiter to get the destroy instance function and just do it. There is a way we can do this right now, although I wonder if it really worth the efforts. But basically, we could load it directly from the dynamic library and use it. We could say, for example, here, I guess, destroy instance or something. PFN destroy instance, I guess. And you could just load that here. So dot destroy instance is equal to, and you would basically do the exact same thing, and instead of vacate get instance proc addr, you would say vacate destroy instance, and of course bfn destroy instance. Let's go. Nice. Or else we're going to return initialization failed. Okay, great. Now after that, if we fail to do this, like we could say here error defer. So if an error happens, if we basically quitted with an error, but hold on, no. Yeah, gotcha. So let's actually check if that's the error explicitly. Okay, so if instance.dispatch, and we're going to basically get that vacate I here. Now if that's the case, now if that was successful, then we can defer that vacate I.destroy instance. Else, if that fails for any reason, and used capture. If that fails for any reason, we're going to basically use the loiter destroy instance that we have manually ourselves done it, loaded it, destroy instance, and here it would pass in the instance and null for the allocator. And yeah, pretty much. There you go. But of course, right now I'd like to actually encapsulate this into its own struct. So here's how we're going to do it. Well, const instance is equal to a struct, const self is equal to this, let's go, and then fn init. I wonder if the stream's still fine. Yeah, it's fine. I thought it would be more than 1 hour though at this point. Okay, anyway, init instance, let's go. The init. My brain is melting right now. Okay. Const handle, and I would say this is going to be vk.instance. Expected after declaration. What are you talking about? Oh, sorry, we shouldn't do const here because this is the field, and we would have also allocation callbacks, which is going to be vk.allocation callbacks. Let's go, and there you go. Okay. And I believe we'd probably, but anyway, let's just try to get this right now to the other side. So I would grab this, guys. Const vkb, okay. I would pass them here. Of course, I need the vkb. Which is going to be of type base dispatch, I guess. Okay. And I guess I also need the loiter or what? Yeah, I need both. Yep. Okay, let's get the loiter into. So loiter, Vulkan loiter, let's go. And you would do this. So if instance dispatch dot loid, this is the vki. So this would basically contain the vki for its own instance, because each instance could contain a separate vki. Okay, so it makes sense to store it here. Vki, it's going to be the instance dispatch. Okay, let's go. And defer vk destroy instance. Now if we failed, we're going to use that destroy instance function. Although I'm thinking, should we really do it right there? I guess I should probably instead do it inside of here. But anyway, for now it's fine, I guess. So if we error, we're going to make sure to use the loiter itself to get the destroy instance function. We're going to use that, and then we're going to return an error. Error dot, well, I don't know what error to give here. I guess initialization failed. Maybe. So we're trying to load the instance dispatch. Now if that's good to go, no, we shouldn't do this here, by the way. Right now, and this would go right now into, well, this would go here now. This would go into the dinit function at this point. But I guess I would leave it, but instead of defer, I would say defer. And then of course have this guy here too in the dinit function. Now if somehow we happen to return from this function with an error, it would make sure to destroy the instance. Of course, if it was successful. Otherwise, we're going to destroy the instance and return error initialization failed. Cool. Okay. Of course, here we would get the self. So self.vki .destroy instance, and the instance is self.handle, and the allocation callbacks is self.allocation callbacks. Same thing in the creation function. There you go. We could use this allocation callbacks later on to create a debug allocator, which we could use to basically track Vulkan allocations, like how much memory it's using, etc. So, yep. Now here we don't have self, of course, but we have, well, we're going to get it. But of course this should be optional, right? Isn't it? Yeah, I guess it should be optional. So we would say this, I guess, and it would say, I mean, yeah. So it's gonna be actually a pointer like this. Okay, hold on a second. So I would say this. I should say this. Of course, vk.allocation callbacks. Let's go. Same thing here. So it basically take an optional pointer, which is basically a pointer that could be null, because by default in Zig pointers cannot be null. So yeah, self.allocation callbacks. Now in this case we already have allocation callbacks, and of course here when everything have gone right, we're gonna say return dot and here I would just add a comment, use the loiter to destroy the instance because we failed to load the instance dispatch. Okay. Right. And here I would return .handle is equal to, well, the instance, and the allocation callbacks is equal to the allocation callbacks that we got, and the vki is equal to the vki that we have just successfully loaded. Cool, amazing, perfect. All right, pretty cool, nice. Now allocation callbacks, it would be part of all but anyway, fine, it's fine for now. Okay. So this is pretty much it, hopefully. Well, I do not really see a vkb.dinit function, so I think we don't need that. And other than that, we would create an instance now. So is equal to instance dot init, and here you would give it the vkb, then the loiter, and the allocation callbacks, which I would go with null for here. Cool. Amazing. Amazing. And of course you would say defer instance.d init. Let's go. Nice. Sig build run. And of course we should try this out. And let's go. All works out. Perfect. Yep. Pretty cool. Cool. Amazing. Now we would go with let's see. Now we have to basically enumerate the physical devices that are possible. And we have to, by the way, there's also another struct called info, application info. Now, if you want to specify the API that you'd like to use, if we check out here hold on a second, Vulkan specification, Vk instance, create flags. There you go, Vk application info. As you can see, you could give it the application name, application version, engine name, engine version, API version. Now, this application version, application name, engine name, etc. This is not, very useful for small applications, I think, at least I think, because basically this is pretty much used, for example, let's say, for example, of course, this is just an assumptions. I don't have anything to back this up, but I guess, for example, the game ready driver, you know, when NVIDIA, for example, releases some updates in their driver to boost some certain games or some certain applications. So maybe it's actually identifying those applications, for example, using these guys, maybe, possibly, I don't know. But you could leave this whole application info to null, which would basically result in all of these guys equal to null, I guess. And the API version would by default be the Vulkan version 1.0. So there is currently, at least while I'm streaming right now, there is Vulkan 1.0, 1.1, 1.2, and 1.3. Now, so far as my knowledge goes, if you want to support as much devices as possible, you'd like to go with Vk version 1.0, so the Vulkan version 1.0, especially when it comes to something like phones, you know, mobile phones, etc. They usually only support 1.0, at least the old phones. And usually vendors, like mobile phone vendors, are so lazy to add new Vulkan versions. So if you'd like maximum portability, then go with Vulkan version 1. And if you don't really if you're not interested into any of this, you could just leave application info as null, which I'm doing right here. Okay, so that's just something to keep in mind. Cool, nice. All right, amazing. By the way, if you'd like to use Vulkan with windowing for graphics, etc., you'd like to add other extension, you would like to add, for example, vk.extension info.khr swap chain, I believe. Yeah, there you go. You have to add this one, .name. And you also, yeah, so this is pretty much it. This is the swap chain you would use for the window. But anyway, so this is just fine for us. Okay, cool. Now let's actually figure out, but before that, I think I'm just gonna have a little break and we're gonna be back. Hello, hello, hello. All right, back into business. Okay, well, all right, amazing stuff. One thing I was thinking about is to actually grab this destroy instance and maybe put in it in the instance itself. I think it makes sense. And in fact, it only makes sense when you would like to basically do it here, use it here. So yeah, honestly, let's do that. I'm going to remove this guy from here. I'd like to only keep get instance proc addr there. And you don't need this guy anymore here. Well, we do need it, but hold on a second. So else, if this fails, then we'd like to try to use this way. And to use this way, destroy instance pfn. Okay, let's remove it from here. All right, cool. So if that fails, then we're going to try to, by the way, here it should be self-allocation callbacks. Thankfully I figured that out. Nice. And here what we have, or else return. Well, that means I have to basically, well, I basically will say loiter.handle, I guess. Right, is that it? Oh, allocation callback, sorry. Okay, can't destroy instance const there. And then I would basically say, instead of loiter destroy instance, I would basically try to say loiter destroy instance. Otherwise, I would just return error initialization failed, because, well, there's just no way. We just lost it at this point if this also errors. So yeah, otherwise, if that's great, and then we're just going to use that, and we're going to pass the instance null so we can destroy it before we return the error. So yeah, pretty much. Nice, amazing. That's pretty much it, hopefully. Let's make sure everything works. Found const. So loiter. Yeah, loiter. So can we use that kind of trick that I've done before, where you basically say, let's say equal to loiter, then you would just use that. Let's see if that trick works. It works. Okay. Weird. All right, fine. So I don't know if this is legal, but it works. So var loiter dot handle. Okay, cool. Dot handle dot lookup vacate destroy instance. Okay, pretty cool stuff. So I think right now we haven't missed any bug, I guess, hopefully. Error defer vacate I destroy instance. Nice, 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 nice. Try dispatch Lloyd. Okay, so now we have to figure out how we can basically enumerate the physical devices. And for that we would need, I guess, here enumerate physical devices. There you go, physical devices. Okay, is equal to true, I guess. Alright, and let's try to use this now. So it basically say instance enumerate, well, vki.enumerate, let's see, physical devices. And you're supposed to give it an address to physical device count and physical devices. Cool. So I guess I'm just going to make a new function here, call it enumerate physical devices, which should hopefully return a slice of vk.physical device, I believe. Or it would be an error, of course, as always. And in that case, we would say this. All right, so we don't need this. Okay, hold on a second. Here, I would have a count. So var count, it would be of type maybe 32. We'll see. Equal undefined. And then I could say, of course, I need self. Here, I would say, let me make sure that the stream is fine, though. I mean, mic is on, okay. Just to make sure I'm not wasting my time here. All right, great. Great. Okay. Self.enumerate physical devices. All right, cool. Self.vki, sorry. Enumerate physical devices. And instance. So instance is basically self.handle. Physical device count, you would give it to an address to the count. And by the way, what the type of it? Yeah, it's U32. So yeah, that's true, or that's right. And you would say null at first. You know why? Too simply. First, you'd like to first of all get the count, how much physical devices there is. Why? Because we'd like to allocate enough memory to store that physical devices. So this is what we're going to do now. We need an allocator. So we'd make sure that the caller give us an allocator of his own choice, and by the way, cd.mem allocator is just basically a vtable. Vtable is allocator is kind of like you could say like a virtual or abstract class in other OOP languages. It basically contains some function pointers to an alloc function, to a resize function, and to a free function. And whatever allocator you'd use, like arena allocator, general purpose allocator, C allocator, whatever it is, you can get this allocator, cd.mem.allocator from it, which would basically contains these function pointers. So basically this is used, so you could basically if you use this, you can pass any allocator to your function basically. But anyway, this is kind of like virtual classes or abstract if you want, or whatever. Anyway, in used function parameter. So cool. Okay, right now we're gonna say const physical devices is equal to well, the allocator dot alloc, and here the type is physical devices, so vk.physical devices, and then the n, here you would give it the count, because basically here we have gave the Vulkan API an address to our variable, to our count variable, and since we have gave it the address, it would basically go ahead, it would dereference it and would put the count right there. That's why it said in the find. I basically telling the compiler that you could optimize this, because I don't want to set any initial value here, because I know that this enumerates physical devices would hopefully do that for me. All right, cool. So this enumerates physical device, of course, could fail. So we have to say try, I guess, right? Yes. So try. Results. You're a crack. Go ahead, champ. Welcome, Jose, Gabriel, Geraldo, Suarez. Thank you for the nice comment. It really helps. So, const physical devices Now what we'd like to do, now this would give some result, which I would just, I guess, oh, hold on, what the, it would give a result. So I'd like to just, I think, skip the result. Yeah, like there's no need for the result. Okay, fine. So const physical devices. We just need to make sure that there is no error right there. If there is an error, it would return it. Cool. So const physical devices is equal to allocator.alloc, and then we would basically say error defer. Make sure to always say error defer. And then I would say allocator.dealloc this, well, free physical device. So if some error happens afterwards, before it would return the error, it would make sure to actually go ahead and deallocate physical devices. Cool. Otherwise, if the function returns successfully, then it would basically not free it. Then the ownership of that slice that we're going to return is the ownership of the caller, so he's the one who should actually free it. Okay, anyway, so error defer allocator.free, and then I would call the function again. Make sure to do this. I forgot it last time in the other streams, and we got a whole like undefined behavior stuff, a UB, which was crazy. But anyway, so you have to basically call it a second time, the same function, but this time instead of passing null here, it would, by the way, you still have to pass in the an address to your account, because this time instead of setting it, since you will give it something other like if you give it null, it's the one that will put the count there. Okay, if you don't give it null, in my case I'm going to say physical devices.ptr. In this case, since it's not null, it would actually use this count. It will read from it, not write to it, because it wouldn't basically calculate how much physical devices there is another time. It already have told you, so it's expecting you to give it back that same thing again. Otherwise, you could even go ahead and give it some other count, and it would do that. Like for example, even though you have 3 physical devices that it told you, you could pass in a address to a number that is just 1, and it would just give you a 1 physical device. So yeah, anyway, so that should be it, hopefully. Now you would basically I guess you would return physical devices now, hopefully. Right. I'm just making sure I'm not missing anything. Yeah, seems fine, honestly. Yep. Okay, cool. Now it would say physical devices, so const physical devices is equal to enumerate, well, instance enumerate physical devices, and here it would give it the allocator. Now of course we need an allocator, so here's how you do it. Too simple. General purpose allocator. Most of the community like to call it GPA, but I'd like to always try to name my variables the whole thing. So yeah, general purpose allocator, well, std.heap general purpose allocator. Config here, I'm not gonna give it nothing, and here I'm going to instantiate the type. Okay, cool. And then I would basically say defer general purpose allocator.dinit. Now this would give me a result. I would use std.debug.assert, and I would make sure that the result of this guy is .ok. Okay, it's going to be okay, because if it's not, that means you have a memory leak somewhere of anything that is used in this particular allocator. okay, which is very useful. It would tell you when you have missed something. Okay, cool. And there you go. So we got the physical device, and of course we should always make sure to say defer allocator.free general purpose allocator. But of course after that I'm going to say const allocator is equal to general purpose allocator. Now all the allocators, now there's a lot of allocators out there, but all the allocators have a function called allocator as a convention. Okay, now when you call this function, it would return to you that std.mem, the allocator that I talked about earlier, this guy, which is basically a v table of all the function pointers that allocator gave it anyway. And yeah, now you would pass that general thing. So defer allocator.free memory, which is the physical devices. And hopefully that's it. Now let me see what we have there. std.debug.print, and I would say this and physical devices. Let's see what we got there. Cast discards const qualifier. Yep, because the allocator should be variable. Allocator though, this guy right here could be const, could be var, doesn't matter, but I would recommend just keeping it as const. There's no need to make it var. So fake physical device does not support field. Oh yeah, sorry. So I have to try this out. And what's the problem here? What is it talking about? Oh yeah, so allocator could fail to allocate memory, so I have to try it out, that out too. And what's going on here? Expected mem the allocator. Oh, I have to pass in the allocator right here. Any. Alright, so this is all the functions that we have called because I'm using the API dump layer. And as you can see, it did print something. Let me just make it clear by adding a new line there. And there you go. As you can see, it's a vacate.physical device, a slice of one item, vacate.physical device, because I only have one physical device, which is my NVIDIA GTX GPU, basically. So as you can see, from the API dump, we're calling create instance, it's return vacate success, enumerate physical devices, vacate success, enumerate physical devices once again, vacate success, let's go. And then we're getting our slice, and afterwards it's calling destroy instance. And since, like, let me show you one thing. Now, if you somehow forgot to deallocate something that you have allocated using the general purpose allocator, if you zig build run now, it would fail. There you go. And it would tell you that error GPA memory address, that address have been leaked, you know. And it failed because I made sure to actually that this is okay. If not, it would do this. But if we do this, then it would be fine. Now let me just not have that guy. Let's just switch to the validation layers. And there you go. Cool. Now there's another thing that is very useful that we have found out in the last streams. Like in the previous 4 streams that we didn't use any bindings, nothing, we just did everything ourselves. I really learned a lot, and a lot of other people learned a lot. I really recommend you to try it out if you have time, although it's very lengthy streams. But it's very useful. I also learned a lot in the process, like a lot. But anyway, so for example, if I didn't go through that, I would probably not figure out a lot of these things, you know. So it's just crazy. Like for example, this kind of loading stuff. Anyway. So dot, I remember it's verbose log or something like that. Let me have a look. So if you go into this config, there's a lot of things that you could basically mess with in this config, but if you enable this verbose log, if you set it to true, zig build run, something is wrong here. No, not here. Actually, it's inside the config here. So dot verbose log is equal to true. Let me try this out. And there you go. Right now, it would tell you exactly what allocations have been done, what is being freed, etc. So you can see everything. Let me just clear this out again and zig build run. As you can see, it's telling me that it have made a small allocation, 8 bytes at that address, etc. And here again, it's freed that allocation. There you go. Since it's the same address, I know that it is freeing that one. Anyway, and that's very, very useful. Now we could actually get rid of that allocation. And there is something very cool that we also learned about in the previous streams. Thanks to some other people that have been joining. But we could basically use a stack fallback allocator. And how that works, well, enumerate physical devices. I can say const, let's say stack fallback. I don't know what to call it. Let's see. Stack fallback, yes, is equal to so scd dot stack fallback, I believe, heap dot stack fallback allocator. Okay, here you give it the size. Let's say, for example, in bytes, of course. Let's say size of size of vk.physical device. So basically what I'm trying to do here, I'm trying to make a fixed buffer that would allow us to skip allocation if the number of physical devices, for example, is small enough. It can be actually put inside that fixed buffer. If that fixed buffer is not enough, because that fixed buffer have a fixed size at compile time. But if that's not enough, we are making sure that we have some fallback allocator that we could use. In this case, it would be general purpose allocator, which is a dynamic allocator, which would be great. So size of vk physical device, this is the fixed size that I'd like. Let's say, for example, most of the time, the number of physical devices would probably not pass on that 4, I guess, typically. 4 physical devices, I guess. And then we could basically say dot allocator, I guess. How would you do it? Oh, do I have to say dot init or something? No, you say dot get. Okay, cool. You say dot get. Is there a init function? Doesn't seem like. Okay, so I guess I could just say this then. Ooh, and resets the internal buffer allocator. What? Interesting. So let's call this stack fallback allocator, I guess, and let's try it out. So instead of the allocator, our dynamic allocator, I'm going to pass in this stack fallback allocator. And let's see what's going to happen here. Zig build run. And oh yeah, no, I cannot do it this way because the allocator itself should be a variable, as I said before. And I mean, you could do this actually this way and then just make the whole thing a variable, I guess. No, you cannot, because get takes it like that anyway. So it should be in its own variable, seems like, just like that. And then you'd have const stack fallback allocator is equal to stack fallback.get, I believe. And you would basically pass in that stack fallback allocator, I guess, to here. And let's go. Of course, this should be var. And here we are getting expected one argument found 0. What? Let me make sure I know exactly what I'm doing here. Get function. Yeah, it returns that thing. So what's the problem here? Oh, sorry. Okay, let's remove that one. And zig build run. Now must be const or com time. Oh, should that be const or what? I guess that maybe I have to actually instantiate that type. Oh yeah, my bad. So oh, let me actually use another a function. Actually, it's better. It's much nicer to work with. So you say stack fallback, and then you give it the size, which as we've done, size of vk.physical device. Let's go times, let's say 4 physical devices, for example. Otherwise, if it passes from that, it would just use the fallback allocator, which is in this case will be allocator, the general purpose allocator. And yeah, let's try this one out then. Oh my god, let's take this times 4 here. This should be var maybe. Let's go, but we have some problem. Invalid free, and that's understandable because I'm not using the same allocator to free. And there you go, seems to work out. And notice that it's not telling me that it's allocating this time, because we have enough space in our fixed buffer, so we do not need to allocate anything in this way. Of course, as long as the vk physical devices is less than 4. Now, if we have, let's say 0, then it would use the fallback allocator, and you would notice that because there's not enough space, and you would notice that it's actually right now allocating, as you can see, small alloc 8 bytes. Pretty nice stuff. Pretty nice stuff. Okay, cool. So now we got that out of the way, and we have no allocations in the program as long as you have just 4 physical devices. Cool. What's next? Now we have to get the Q families. So how we would do that? Well, I'm going to go through all the physical devices that we have available. So 4 physical devices, physical device. Let's go. Okay, cool. Used capture. So now we need another function. So let's go to the dispatch. So instance dispatch, we would say dot enumerate. Let's see, what is it called? Actually, maybe get Q family or something. Yeah, get physical device, I guess. Q family properties. Let's go. And just be careful with the autocomplete, because this should be vk physical device Q family properties, not properties 2, because there's another function which have a 2 here, which is basically from another extension, which basically gives you more properties. But anyway, so is equal to true. Now we have loaded that one, and here we would say okay, let's see. Const Q family properties, or let's try to use it. So how we would do that? Well, instance.vki.get physical device Q family properties. Let's go. So here you're passing the physical device, which we have from the loop, and then the Q family property count. So basically the same thing that we have done earlier with enumerating physical devices, we have to do it here. So we basically have to get a count there, and then here null at the start. So yeah. Do you think we can maybe make this into its own thing, like into its own struct? just to make it more convenient, maybe. Not really, there's no need. So count, okay, let's grab var count u32 equal undefined. Okay. So that what it would give me, it would give me none, of course, because it would basically just, so this can't error. So I have to basically right now try to allocate enough memory with that count. So let's do that now. Const, I guess, q family properties is equal to allocator. Now I would use maybe the stack fallback allocator, so we don't need to allocate anything. Okay, alloc, and here I would say q family properties vk.q family properties, and the n, the size is, well, the count that we got. Amazing. Rate. Now I would make sure to free that stuff. Defer allocator.free q family properties. Now, of course, make sure the allocator that you use should be the same as the allocator that you use to free it. Of course, this is obvious, but you could easily forget about that. And other than that, now you would basically go through all the Q families on that physical device by doing this for Q family properties, Q family property. Okay. Now we could basically, for example, debug, print, and let's say, for example, Q family property dot, I guess, Q count, for example. Let's see how much Qs, and then let me make sure to add a new line there, and let's see what we get now. It's not indexable and not a range. Q family properties. Oh yeah, I forgot. Okay, well, man. And of course I should make sure to have a try there. Cool. By convention, by the way, the deallocation or the destructure functions in Zig by convention shouldn't return anything. They should, at least they shouldn't fail. So you're usually going to find a void there, so you don't have to try them by convention. But there's nothing stopping you from doing otherwise, though, depending on your use case. But instance get physical device properties. Okay, and here I have to pass in the pointer. There you go. Cool. Zig build run. Expected to, oh yeah, I always forget. I need the tuple here. And there you go. So right now it's telling me that an allocation happened of 96 bytes. And it tells me that there's 16 queues in the first queue family, the two queues in the second one, 8 queues in the third one, and 1 queue in the fourth one. And as you can see, there's an allocation because there's not enough fixed space. Although, oh my god, well, I missed one thing, I believe, here, which is the fact that, hold on, let me see. Let me just see one thing real quick. So this function both fetches an allocator interface to this allocator and resets the internal buffer allocator. Well, but we only reset in here, I believe, so that's fine, yeah. But just be careful if you're going to use this .get function twice, then be careful because that would reset the internal buffer, seems like. I mean, let me have a look into it. Yeah, fixed buffer allocator.init. Let's go. Okay, I think it should be fine for me here in this case because I'm only using it once. But now there is two ways of doing this though. We could either create 2 stack fallback allocators, or we could create 1 stack fallback allocator for both. So I think I would go with the 1 stack fallback allocator for both, and you know why? I'm basically because I think so we're kind of trying here to estimate the typical maximum or the average maximum of, for example, here physical devices we said 4, you know, and the key families I would just say 8, for example, although it would probably not go to 8 most of the time. Most of the time it would only go to 5, for example, but I'd like to always round up a bit. But I can say plus size of vacate of physical, well, not physical, key family properties. But of course I would go with 8 right here. And I'd like to go with 4 here times that, just for aesthetic reasons. Hello Travis, welcome back. Welcome back. So just to give you some context, we have actually, this is a new series. So we have explored the Vulkan API with Zig ourselves without using any bindings, nothing. And we learned a lot of stuff, but surely it wasn't so maintainable in the long run because there's just a lot of things to manage. So I'm starting a new series, or new series of streams, basically, where this time we have a goal of basically creating a compute application, okay? And also we're using vacay, well, we're using this extension, well, not extension, binding, sorry. This guy, well, not this guy, hold on. This guy, okay. So we're using this guy, Snektron / Vulkan-zig. So far it seems to me, from looking into Snektron stuff, he seems like to know what he's doing. So we're going with this one. And of course I'm going to start. Watch. Okay, sure, all activity I guess. And there you go, fork. Okay, so that's basically what we're doing. You can rewatch the stream. There's a lot of things that we have done here, but anyway. And by the way, if anyone wants to contribute, you're welcome. So, all right, fine. Now let's get back into it, where we was. All right. So as I said, well, there is 2 ways of doing this. We could create 1 stack fallback allocator, and we could use it for both, or we could use 2 ones. Neat, seems like good choice. Robin is good and a long-time activist contributor. Yeah, it seems like. Also, I've managed to see that he's working currently on the Zig SPIRV compiler thing. And SPIRV, by the way, is basically kind of like the thing that we compile to, the compiler that we use to compile shaders in Vulkan. So it seems like he's very knowledgeable. That's why. So anyway. Yeah, SPIRV backend, right, exactly. So 4 times. So I'm going with this one where I basically have 1 stack fallback, and my reason is for this design decision is the fact that basically if we have only 2 physical devices and we're kind of given a margin of 4, then if there is more than 8 key families, for example, key family properties, then this guy would compensate with the free space, okay? So basically, you would only have 1 allocation or none. But in the case of 2 stack fallback allocators that are separate from each other, you would basically, you can have either 0 allocations, 1 allocation, or 2 allocations. Well, honestly, you could still have 2 allocations in using 1 stack fallback though, but at least you're trying to compensate with one of them, okay? So yeah, pretty much. Anyway. All right, so hopefully that's pretty much it. And let's see now if it will allocate or not. It seems to still allocate for somehow. I think I'm missing something here. Plus size of 8 for, yeah. What's going on here? Defer, try, Q family properties count. I don't know honestly why it's still allocating that thing. Let us try something very big, I guess. Let's say for example 16, I don't know. That's too much. Okay, this time it's not allocating. Weird. But 8, it allocates, right? What? I bring it back into 8 and now it's still not allocating. Weird. But anyway, so I have 4 Q families. Zig build run. Let's try it, see if it will. Okay, I also have only one physical device. Now, let's say physical devices is 0, for example, but I have 1, okay? Now, I still, like, if I do this right now, it would allocate for that physical device because it doesn't have enough space. But if I have some extra unused space from the what we allocate to the Q family properties, it would use that then. So you don't have to allocate this time. There you go. So that's my basic logic for choosing this one for this thing. So yeah, pretty much. Okay, cool. So this is it. Now we have to choose basically a Q family. Now I think I would basically put this into its own thing right now. Let's go, I believe, to here. Now let's say fn select Q family. And it's supposed to return either an error or a slice of vk.physical, well, not physical, key family properties. Let's go. And here, of course, you're supposed to give it physical devices. And I could have just used self to use this enumerate physical devices here, but I'd like to try to keep every function doing its own task. So yeah. It could be an alignment issue when making the allocations rounding up somewhere. Yeah, possibly. But when I run the next time after I edited that thing, it was just fine somehow. I don't know. But anyway, select Q family, physical devices. And here this would be a slice of vk physical device. Let's go. Cool. And the other thing that we need is the instance, which is basically self, and again self here. And I also need an allocator in this case. And the allocator would be a cd.mem.allocator. Now here we're basically creating a stack fallback allocator, but actually we should get it from here. Oh, but we're using it for 2 things. Interesting. Well, I would just go with allocator anyway. Yeah. And the Q family property. Now we're getting the Q family property. Now we have to do something. Now a better way, maybe like a more general way of doing this, could be lambdas. Okay, so now there is no syntactic sugar for lambdas in Zig. but there is a way to do it using structs, I think. So you could basically, for example, I guess, never actually used it before. This is the first time I'm gonna try it, but basically you could, I guess, say, and oh, also something that I should not forget about, as I did before in the previous streams, is that instead of the fur inside of here, you would say error the fur. Okay, so where? So after allocating, I should make sure to say the fur, and then queue family properties. And why there was physical devices though here? Hold on a second, what? Oh, never mind, it's fine. Okay, fine. So here, allocator. And is there something else here? Oh, actually, in the case of this guy, we would just deallocate it, I think, right? Isn't it? Queue family properties. We're getting all the queue family properties. Now we could make use of that area allocator thing here. But anyway, this is fine for now. Okay, cool. Defer allocator.free queue family properties. Oh man, I've done it twice. Well, something is weird I'm doing here. Defer. Okay, there's no need for this. Okay, it's fine. All right. So now, what we should do, we would get some kind of function pointer here, and what it would be, well, let me see some function pointer just so I get some, I don't know what to call it anyway. Whatever, doesn't matter, any function. I just want to see how it's done. So you'd say const fn like this, q, whatever. So we could say filter, maybe const fn. Does this work like that? Or I could say, for now, just call it filter func, and then I can say const filter func is equal to that stuff. But I don't remember how you do it. Function pointers, zig. Well, actually, let's go to the documentation. Okay. There you go, const fn, for example, this. So let's try this out. For example, if I put it here, would it work? Yes, seems like. Although it's probably better to do it in its own constant. But I guess fine for now anyway. Let's try this out. So you basically have a filter function. And I guess it would give you, let's see, it would give you a queue family property, I think. So queue family property, how you would do that? So vk.queue family property, what? Yeah, properties. I think. Well, I'm calling it property, but it shouldn't be that way. Queues family. What? Queues family properties. I guess maybe I should add a queues right there or something. Queue families. I guess, Q family's properties. And then this would be Q family's properties, of course, Q family's properties. And finally here, Q family's properties. And this is actually Q family properties without the S in family. Because here we basically have several Q family properties. But that's just English, I guess. I'm not so good at English, but anyway. So, Q family properties. And you should basically give it some kind of Boolean value. Right? And then here we could basically say if filter, and we would pass in the Q family properties to the lambda, then, well, right now we would return a Q family. Now I would actually have another struct called Q family, which would hold two things, the physical device and, as we did before, and then the Q family index, to be exact. And this will hold, I guess, a U32 or a usize, depending on how you want it. I would go with the usize, maybe, honestly, I don't know. Yeah, fine, anyway, and we'll see. And then here I would say if filter, so if it returns true. Oh, filter? No, not filter. I should call it something else. I should call it selector. Let's call it selector. Okay, selector, I guess. That makes more sense in this case of what I'm doing here. So selector, and you would give it Q family properties. Now if it selected it, then it would return a vacant Q family. Sorry, a Q family. What I'm doing here though? No, I don't want to do this. Although honestly, we should probably separate that into its own function. Right. Yeah, honestly that makes sense. Or isn't it? Hold on, what? Well, it's fine for now anyway, who cares? So Q family, so this would give an error or Q family. And here we return dot. So in this case, physical device is equal to the physical device from the loop. And so basically here we're looping through all the physical devices that have been enumerated and all the Q family properties in each of the physical device. And whenever we find the Q family that we want, we're going to basically return the physical device that we were in and the Q family. So we're scanning through all the physical devices and all of its Q families. Anyways, so the Q family index. Now here, what we need for the API to get our Q is the index, not the Q family properties. The Q family properties is just the way that we select which Q family. So anyway, so to get a Q family index though, we would need to add another guy here. Let's see, 0 point, and then I would say Q family properties, Q family index. And there you go, Q family index. Let's go, nice and nice. There you go, cool. Amazing. Amazing. So I think that's pretty much it. Now the thing is that you need to figure out is how do you create lambdas without having to basically create another function somewhere. So let's see how we can do it. So instance.select Q family, you give it the physical devices, which we got. You give it an allocator, which we have the stack fallback, I believe, and then you give it a selector lambda or function pointer, whatever it is. So here's a trick I found, which is to basically, I guess, do something like this, and you would put a function here, I think. For example, selector, right? And this should of course give a boolean, and you're going to get the Q family properties. And you'd basically need to return true or false depending on those key family properties that you got. And here, after the thing, you know, you would just say dot selector, I believe. Now we could say Q flags. Okay, let's check out on the Q flags, and we need to make sure that it supports compute. So how we would do that? Well, so let me have a look into the Q flags stuff. So you would basically say if its compute bit is true or false. This is how this binding does it. So you just say dot compute bit, and just like that, I guess. So yeah, maybe. What's wrong with this guy? I honestly don't know. But look, there's an easy way for now. We could just do it like this. You basically have a function, and let's just try this out real quick. And you would just give it the selector. Just like this. And here you would get an error or a Q family. So const Q family is equal to that guy, and let's try to print it hopefully and see what's up with it. Q family, and let's go. Function parameter shadows declaration of selector. Oh yeah, I guess let's call this for now selector lambda or something, whichever floats your boat. Oh yeah, so if we don't find a Q family at all, so after the loop, the whole loop, they would basically return, well, null, because we didn't find one. And of course that should make this an optional. Okay, so either we find one or not, pretty much. And zig build run. I guess we have to, yeah, allocator. Okay. All right, because it's optional, so I'd have to say any, for example, I guess. Oh, it's already have been done, but okay, I need a new line. As you can see, it's finding it. It's finding some vacay physical device, and it's giving me the Q family index, which is interesting. Now, the way that I talked about is, I believe you have to actually say struct, not that guy, and then you would say if n selector, and then Q family. So basically the same thing as we have here. Okay, but instead of lambda, I would just remove that. There's no need, I guess. And then you would, after the struct, you would say dot selector, I believe, if I remember well. So that's just a trick. Zig build run to create lambdas. And it actually works. Let's go. So this is how you do lambdas in Zig without having Zig actually do lambdas. Just because of the Zig struct design. So even a file is a struct. So you'd basically create an anonymous struct. You create a function inside of it. You can name that function whatever you want, and then you basically take that function dot selector. Or we could even call it lambda, just to make sure that it's clear that it's a lambda. And there you go. Done. Interesting. So yeah. Amazing. Cool, cool, cool. Or we could even go with a mathematical kind of notation. Call it F. And there you go. But no, let's just go with lambda. I think that's nice. So anyway. There you go. So we got a key family now. And of course this would give us either null or a key family. So what we should do when we don't find a key family in this case, well, I guess we would just return an error, or else return error.no suitable Q family, right? I think so. Cool. Let me just make sure the new thing works, honestly. Let me make sure we have a new line there. And yeah, it works. Perfect. Perfect. Cool. So now what's next? We got a key family. Now we gotta create the device. Okay, cool. So here we would have fn, I believe, create device. Or no, I'd like to not do that. I'd like to have a struct. Okay, so construct device is equal to a struct. Let's go. And actually const device equal to a struct. Cool. That's very nice. Very, very nice. And we're still not making any allocations, by the way. Cool. So const device. Okay, cool. Const self is equal to this. And we're gonna have an init function which would basically return. By the way, let me make sure I'm using self everywhere. Okay, let's make use of self here. Okay. Vulkan loiter. We're not making use of self for some reason. Let's go. All right, cool. Now let's say either an error or self, of course, as always. fndnit void. Nice. So now let's try to do it. Let's try to do it. And use local constant. Okay. So let me zoom in a bit here. So how we're going to do this? I think first we need the instance, right? So, well, instance. Let's go. Let's see how to do this. So instance, I believe. So now we have to load some function, of course. We have to load in the instance dispatch. we have to load. Oh, by the way, I think I'm missing. Oh, never mind. Okay, it's fine. Okay, create device. There you go. Is equal to true. And dot destroy device is equal to true. Let's go. That's the things that we need right now. And also we'll need the git queue later on, I believe. Git device queue is equal to true. Okay, cool. Now we would basically function init instance.create instance, vki.create instance. No, what I'm doing, create device. All right, here you have to give it the physical device that you have chosen and the create info and the p allocator. For now, we're just gonna hard code that the device would take only one, would create only one queue. So yeah, so I would just get a queue family here, just to keep things simple. And here I would say queue family dot physical device that is chosen. And here in device create info, I could say this. For the allocation callbacks, as always, well, allocation callbacks. Oh, here, I should do it here, okay. Then pass in the allocation callbacks, cool. All right. Create device and the init. We would also say, well, but before that, let's see what we got here. Create device. This could error, of course, so let's try it out. And well, I guess we would return what we got. Or in fact, there's no need to try it out. I guess we would just return that stuff, maybe. So here in create info, now there's a lot of things that we could give there. So S type is automatically done for us by the binding, pnex, null, flags, nothing. So the only thing that is interesting here, I think, is queue create info count, queue create infos. I believe device layers and extensions are probably deprecated at this point, I guess. But yeah, p enabled features, I'm just going to let that be null. All right, so this is the only interesting ones right now: queue create info count and pq create infos. Cool. So dot queue create info count is equal to 1 for now. Or let me just make use of a slice, honestly. So queue create infos.len and .queue create info, well, pq create info. There you go, is equal to queue create infos .ptr, and let's go. That's all we need. Now const queue create info count, oh, well, infos, is it equal to, well, again, a slice, I believe. Like this, right? So this would be a slice of, let's see, a slice of vk.device queue create info. Let's go. And now the only queue for now that we're going to have is, well, let's see what we need. So there is flags, which I guess I'm not gonna use. There's only a protected bit right there. Queue family index, which I'm going to use. And there's queue count and queue priorities. So I'm basically going to create a queue priorities kind of slice. And that would be, yeah, and that would be enough to determine these two guys. And the queue family index, I'm gonna get it from the queue family struct. So, okay, cool. Dot queue family index, let's start right that, is equal to queue family dot queue family index. Honestly, since it's already called queue family, I guess I would just call it index then. I mean, yeah, makes sense. So let's just call this index, honestly. And there you go. But of course we have to change some things now. Let's look for queue family index dot index, where we're using it again. Yeah, that's all. So dot queue family index equal queue family dot index. And then finally, I guess, yeah, queue priorities. Okay, queue priorities, family priorities, or anyway, I don't remember. Let's see. So it'd have queue count and PQ priorities. Now here I would say queue priorities. Priorities. Oh yeah, I knew there was something wrong with that. I didn't knew what was exactly the problem, but something looked wrong. Anyway, so dot len. And here queue priorities dot ptr. Let's go. And what's wrong here? Anyway, let's just create a queue priorities. Well, it will be just basically this and this and this. I think maybe I have 32. And anyway, I'll just do it this way. Not sure if it's F32 or something else. Yeah, F32. And that would contain, doesn't matter since we only have one queue currently, doesn't matter what you do here. I mean, that is just the priority. So, well, when you have two queues, one queue, doesn't matter what the priority, you only have one queue that you're occupied with. So if you have one task to do, well, doesn't matter what the priority of that task, you only have one task to do. So yeah, key count. So something is wrong here. I'm not sure what's wrong. Expected field initializer. Oh, equal. Okay. And hopefully that would work. Let's see. But of course I have to create a device to find out. Const device is equal to, well, device.init. You would give it the instance that you got, and then the key family that you got. And then finally, I guess, the allocation callbacks, which I'm gonna go with null for now. and then it would say defer device.dinit. Cool. But I'll maybe make sure at least that we have self there. Of course I forgot that we should actually have store the allocation callbacks and the handle, etc, etc. So let's make sure to do that now. Allocation callbacks and then the handle, and yeah, the handle. And oh, I think we also have to, yeah, we have to load the vkd, which is basically for device, the device wrapper. Okay, we'll see. I'll see about that. So handle would be vk.device, I believe. Yep. And so here what you would do, instead of returning just this guy, you would actually say, I guess, const device is equal to this guy. But of course try to do that. Then at the end of the day, I'm going to try to return device. But after device, actually, I need to kind of do a similar thing with that I've done with the instance, basically. So you would have the device dispatch, and you would also have I basically do that kind of trick that we've done, for example, here. Although honestly, I wonder if it does really. But anyway, fine. But if you really want to do it correctly, that's what you gotta do. So I guess let me try to kind of copy this guy, because it's going to be basically a similar thing there. Yep. So after trying to create the device, so I shouldn't say try here, because depending on what's going to happen there, we're going to do something different. Or isn't it? Right, what I'm doing in instance though, hold on a second. What? Oh yeah, that's all right, gotcha. So there should be a try there. I mean, if you have failed to create the device, then it's game over, you know. So, but if you were successful to create the device, but then you weren't successful to get the dispatch, then you cannot get the destroy, like the function that would destroy the device. Now that would mean that you have you're basically leaking a device, okay? So you should try to use the previous dispatch to hopefully get it. And if that fails, you have to maybe try to get the other previous thing. So yeah, kind of get crazy. We'll see. Anyway, so first of all, I need to create a device dispatch though. And we should not get these guys here. So just create device in the instance dispatch, then you would basically create a const device dispatch is equal to vk.device wrapper, sorry. And then here you can do this, and then destroy device is equal to true. Let's go. And let's see how we're gonna deal with that. But as I said, oh well, to be able to do that, we have to again to load it from the loader, because we cannot sadly add that into the instance wrapper. So I have to use the base dispatch. We have to use the loader and try to do that. Oh yeah, gotcha. Gotcha. I wonder if there's a simpler way using the binding. I didn't really explore the binding that well. I'm basically doing it live. But anyway, we'll see. So after this, we would use the device dispatch, and we'd try to load, and here we would give the device that we have just created. And here we needed the loader, of course. Now, don't we have the loader inside the instance or not? No. So we're not storing that because we don't need it just in the init function. Okay. So yeah, we have to also, to init a device, we have to also add the loader here. So how we're gonna do that? Well, how we're doing it here real quick, just to be consistent. Okay, after the vacab. After the vacab. Oh, okay. The base dispatch. Well, we could just tell it to give us the vaki then. Let's see. But anyway, yeah, honestly, we only need the vaki. But anyway, fine. Anyway, so here, let's get the loader. And for the loader, but honestly, if we really don't need that guy, let's just do it this way, I think. The vaki, just to be consistent, I guess. As long as, of course, you don't need anything from the instance. I mean, why bother? So vaki. Here the loader, Vulkan loader. And this would give us the vkd. Okay, which stands for Vulkan device. Okay. Error defer, vki destroy instance. Well, alright, this is gonna be interesting. So if we have managed to load in the vkd, we're going to use it to destroy the device. But of course, if an error happens before we exit, and of course we would give it the device. And now, of course, in the dinit, we are going to do something similar here. So vkd destroy device. Of course, self.vkd.destroy device, and you would pass in the self.handle here. Here would pass in the allocation callbacks, which is basically self.allocation callbacks. And I wonder if I've done that before. Yes, I did. But I need to store the vkd2 just to be consistent. Yeah, I added it there. Cool. So vkd is of type instance. Now it's important that you, I guess, have a vkd for each device, because let's say, for example, somehow you created two devices, okay? And one device is from, let's say, an Intel. Like, let's say those two devices have multiple, like, have different drivers. Then, well, you won't have the same addresses for each pointer, function pointer, you know. The first device would have pointers to its own driver, and the second device would have pointers to its own driver too. So yeah, that's why I'm doing it this way. I'm doing it this way. So anyway, vacay. So I'm trying to think about when you would have multiple things of something, but yeah. Anyway, here we would have base dispatch, or should I say device dispatch, right? Device dispatch. Let's go. That's the vkd, vkd. So device, allocation callbacks, vkd, Okay. Now here, now the thing is, what happens if you couldn't load the device dispatch? Then, well, we are going to try again to use the loader to hopefully destroy the device in this case, because we failed to load the device dispatch. Okay, so destroy device. So here we're going to try to use the loader to get the vacate destroy device, and pfn and destroy device. Okay, and now we would. I wonder if any C implementation would really worry about such things, man. But anyway, destroy device. Cool. But here, not null though. Isn't it here the allocation callbacks, I guess? Yeah, the allocation callbacks. I might actually yeah, I forgot to do it. Oh my god. Okay. Let's go. Well, we're only going to find out if this code works when someone is unlucky enough for the loader to not load for him for some reason. So anyway, destroy device. Cool. We should probably give like distinct errors for each case. For now, I'm just returning one error, just so I don't stay here like this trying to figure out another name. Okay, so destroy device. Let's go. Okay, hopefully that should work, maybe. Only way to find out is to try it. And of course it never works at the first try. Expected type found const tuple contime float, because this should be as if32. Why it's comp time? I guess you don't need that. Maybe I have to actually do it here. I'm missing something here. So we have a slice, I guess, of const if32. Is that really does that really matters? Oh, this is kind of like an array, I guess. But why I could have not used a slice then? That's weird. I'd like to not do an array, but a slice. So, what's wrong with this? I guess that works now. I just need the const. Now this one is, I believe, the same exact thing, I guess. In where? In queue create in. So expected type u32 found u size, but where exactly? It's not telling me where exactly, but I would think it's here. Queue count. Int cast. And here would say u32, and you would give it queue priorities.len as always. Okay, let's try this out. We still have the same problem, really. Expected type u32 found u size. What's wrong here? Oh, by the way, we have another expected 3 arguments. Yeah, instance.vki first. And then afterwards, I guess the allocation callbacks maybe? Is that it? Yes. Let's try that one out now. Oh, it's raining. Cool. Expected type, main Vulkan loiter. Yeah, I think I need the loiter here first. Oh man, nice rain. No field or member function named dinit. Because I have to try this stupid thing. Now we're back into the same problem that we had, I guess. Clear. Guessing index is a u32. Index u32, which index? So it's telling me here, but what? Really? Oh, I guess maybe it's talking about this guy. Stupid stuff. Anyway, let's try this out. Same problem. Oh, index. Yeah. Well, what about Q count? Does that need it? Though? Q count. Yeah, Q count is also u32. The index is also u32. Well, that makes sense. So yeah, good catch. Int cast and the index there. And let's go. Oh man, very nice rain. So calming. Thank God. Expected type, vk instance. Okay, so I guess maybe in create Lloyd, I'm passing in device, right? I guess here I should pass in get the device proc address, right? Yeah, I think. Get device proc addr. Okay. And because there is basically get instance proc addr and get device proc addr, right? Yeah. Okay. And now I need to figure out Vulkan loiter. Okay. sorry, get device proc ADDR. I believe that's the thing. And then I would basically do the same thing here. I'm glad we tried to roll our own raw stuff without the binding, otherwise I would have not understood how to do any of these stupid things. Oh man. Okay. Get device proc ADDR. Gotta do it the hard way, or you'll be stuck. That's why it's good to know what's happening in the under the trunk. So when your car break down in the desert, you know exactly how to to save yourself. But if you're using a fancy binding and a fancy high-level language and something breaks down, well, just die at that point. So get device proc ADDR. That's what's happening right now. I'm using the binding, and hopefully, thank God that I know exactly how this stuff works in the background. Or at least what it takes to make it work. Anyway, pfn get device proc ADDR, vk get device proc ADDR, let's go. Alright, so this maybe should work. Maybe. And it seems to be fine. At least we don't get any bug. Like it does compile successfully and run successfully, but if it's doing it right, yeah, who knows. Let's check the API dump. At least the validation layers didn't tell us anything, so that's a good sign. Now let's see what Vulkan functions we're calling right now. Cool. So there's a lot to check. So vk get physical device, vk get physical device key family properties. Cool. Oh yeah, I forgot to actually describe how key family stuff works in this stream. I did that in the previous live streams, but I should redo it right now, I guess, because of the people that didn't watch those streams and they're starting from scratch with this one instead. Using the binding, of course, although I kind of recommend to check on how things works on that one. But anyway, so we're calling create device. It's returning vacant success. Nice. Cool. And destroy device. And as you can see, destroy device and then destroy instance. Perfect. Seems all good. Of course, there's probably some bug lurking around that I didn't notice, I guess. I don't think it's perfect, but anyway, I'll see. Okay, so I was talking about key families. Well, let's just do a little review on what I've said earlier in that stream. Which is, so basically, as long as you install that thing, you can now, okay, we have installed it in that stream. Okay, so basically it's called Vulkan Caps Viewer. Okay, so check this out, it's very useful. Vulkan Caps, Vulkan Hardware Capability Viewer, sorry. But anyway, so this is the actual repo, Vulkan Caps Viewer. Let's go. So you could even check out the code. Man, beautiful rain. All right. Vulkan Hardware, let's go. This guy is pretty cool. He made a lot of stuff for Vulkan. He's made this Vulkan hardware capability viewer. He also made some examples of the Vulkan in the official Vulkan repo. And there's a lot of cool things that he made. So, and the Vulkan database, pretty cool stuff. So I'd just link for you these stuff. So you could also use this Vulkan GPU info database, which you could basically look for any kind of device that, of course, someone have reported, and you could check the Vulkan stats of it, you know, and you could, of course, and see like the properties, the features of that device, in whatever extension you'd like, in whatever version that you'd like, I guess. You could check the extensions that are possible in that device, the formats, the queue families, the memory, surface, instance, etc. And for me, right here, I also installed this Vulkan Caps viewer. So I would go into it. I used my package manager, the AUR to be exact, but depends on what OS you have. And there you go, this is it. And for me, device is already presented database. If you see another message here, you could contribute to this database by basically clicking upload here to upload a report of your own device, the driver, version, driver, etc., and platform, of course. So yeah, of course, if someone did that yet, for me, I just did that in the previous streams anyway. So you can find the properties here, and there's a lot of cool things that you could check out, and you could filter here. There's the versions right here, and here's the features that are available for my device, and here you can select your device if you have multiple ones, and here are the extensions and formats, the key families, memory, surface, profiles, instance. Now what's interesting here is the key families. Okay, so basically each device would have a set of key families. Let me just show you. So in my case, in my device, NVIDIA GeForce GTX 1650 on Linux, because even the platform matters, and on my current driver, which I don't know exactly which driver, but anyway, like which version should I say. So basically all this stuff could change depending on, as I said, the platform. First of all, the device, then the platform, is it Linux, Windows, or what? And third of all is the driver version. Okay, which driver and which driver version. So these three things, I believe. And so in my case, I have 4, and there's the first one, and this is the flags. Basically, each queue family is basically kind of like a group or a set of queues that are capable of something. Okay, for example, the first group or the first family, whatever you want to call it, they have some flags. The first family supports graphics, it supports compute operations, it supports transfer and sparse binding. And just to keep in mind, if a queue family supports graphics or compute, then it implicitly supports transfer. And honestly, I never seen a queue family that doesn't support transfer. I mean, I think it's probably pointless if it doesn't support transfer, but I don't know. Don't quote me on that. I didn't read the whole Vulkan API documentation stuff. Anyway, it's so big, it's huge. So there is, for example, in queue family 0, as I said, support graphics, compute, transfer, and sparse binding. Then there's 16 queues inside of it that you can request, and you could think about queue as like kind of like a thread, you know. So each queue, we'll get to the commands and stuff later on. You'll understand more. But anyway, and there's this transfer granularity, and anyway. And there is supports presentation. If you want to present to a window, then you'd have to make sure that the key family also supports presentation. In this case, the key family 0 basically supports everything, seems like, and it also supports presentation. Of course, this changes depending on the device. That's why you have to, in your application, you have to basically go through everything and check out which one makes sense. Okay, and the second one, in this case, only supports transfer and sparse binding, and only there's 2 queues in this one. and supports presentation. False. It doesn't support presentation. By the way, if the queue family supports graphics, or I'm not sure about compute, but basically graphics at least, then the transfer granularity is 111 always. And this matters, this numbers matters when you want to use it to transfer stuff, because I didn't really understand it very well, but at least from my understanding until now is that if there's, for example, 8 by 8 here, you can, like if there's one by one, you could basically give it, you could even transfer 1 pixel, I guess, maybe 1 by 1 pixel image. But let's say, for example, there is 8 by 8. For example, here, this key family only supports transfer. It doesn't support graphics. So this could be something other than 1. So you have to make sure, if this is 8, I guess, at least from my understanding until now, is that you have to make sure to transfer at least 8 by 8 image, I guess. But it could be wrong. I never really tried to work with this one yet. But anyway. As you can see, this one doesn't support presentation. The third queue family supports compute, transfer, and sparse binding. And you have 8 queues. And it supports presentation. Queue family 3, transfer, sparse binding, and video decode. This is new. When I was just started learning Vulkan, this wasn't the case. I only had 3 queue families at least listed. But anyway. Supports presentation. False. And there's only 1 queue in this one. Okay. Interesting. Now, there's one tip that I could give you also, is the fact that the less flags you have in a queue family and the less queues it have, the more specialized it is. I don't think this is in the specification, so it's not entirely it's not necessarily true. This is kind of like just a heuristic that you could follow. So you could, for example, sort the queues by how much the queue families by how much queues there is and how much flags they have. And then the less queues you have, and basically, so the queue family 0, it would have the less queues and the less flags. And so you would start scanning through and looking for the best queue family depending on how specialized it is. So for example, here in our case, since we're only doing compute, we should probably select queue family 2 for best performance, I think. Especially if you're using, let's say you have graphics and compute and you want to do both in parallel, then you could basically take queue family. You could make request a queue from queue family 0 for graphics, and then request another queue for compute in queue family 2. But yeah, something like that. And for example, here in the transfer, there is something called a DMA, I believe. Not DMA. Hold on. GPU transfer unit, I think, something like that. I don't remember the exact name. It's kind of like DMA, or I don't really remember exactly what is it called. Maybe DMA. Yeah, I think it's DMA. The hardware assisted direct memory access, maybe? Yeah, I think so. I think it is the case. So if I say GPU DMA, but the gist of it, basically, at least from what I understood, is that a GPU could have a DMA, which is basically kind of like a dedicated unit for transferring stuff. So if you have large textures and stuff, you could basically request another queue from that queue family. Like in this case, it would probably be the queue family 1, since it's have less queues. So it's probably the 1. You would use it to asynchronously, so at the same time you would load your textures while your graphics operations are going on. But yeah, stuff like that, pretty much. So this is just a little review, I think, on how you would how this stuff works. Anyway, So there's not a lot of time left though, but I think we may be able to do a bit more. Okay, so right now we got the device down and we got the Q family down. By the way, what do you think? Should we do that sorting thing? I guess I would. Let's see. I never really sorted something in Zig before, so I don't know which function I would use. Maybe let's check the std documentation. Zig std docs. Let's see if we can do it. Although, let's see. So there is std.sort and there's also std.mem.sort. In stable. I'd like a stable sort, I guess, maybe. Depends. So there is a difference between stable sort and stable sort. So stable sort, if let's say Q family is equal of value as the other Q family that is next to it, the sorting algorithm would make sure to not change their positions. But an unstable one doesn't really guarantee that. But of course, an unstable one is probably would be much more performant because you're giving it another degree of freedom, you know. So that's how it works, I guess. Okay, so let's check this out. I never really looked into this before. Okay, so you give it a type. I think std.sort is being moved to std.mem.sort, very recent. Let's check where it's sort here. There's no sort here. I don't know why it's... But anyway, I think this is the only sort function as Travis said, I guess. So, so you give it the type, the t value, and then items. It's a slice of that type that you gave. In our case, it's going to be Q family properties. So the t would be Q family properties, and then items would be a slice of Q family properties. I don't know what is a context. It seems like a comp time, not comp time, but anyway, context something. And then we have a comp time less than function. So it's going to be a function. And you would give it a type of context. The type of context. So it would infer, okay, I guess. And then you give it, it would basically give you two things, two Q family properties, and then it would give it a Boolean telling it if that thing is less than that thing or not, I guess. Maybe. Let me see if there's some test that we could check it out. Okay. So there is something called source context here. I don't know what is this context. Let's look for, hopefully there's a test for it. Doesn't seem like, sadly. But it's using this block function, std.sort.block. And it seems like it's just redirecting to it. So, okay, .sort.block. There you go. So stable in place sort, on best case, on log n worst case. O1 memory, no allocator required. Sorts in ascending order with respect to the given less than function. The algorithm only works when the comparison is less than or greater than. Okay, so you could say, I cannot say equal to the less than function. What is the context though? So it seems like it's using just void literal that. Okay, I guess let's try it out, maybe. Let's try it out. So, well, where we should go. Unless you need to provide some states. Oh, I see. I don't think we need that. So select queue family. So here we're grabbing the queue family properties in an array. Okay, in an allocation. And then after that, yeah, here we're actually populating that thing. Okay, so after this I should sort that guy in place. So std dot mem, I guess, dot sort. Well, doesn't seem like it's there. So dot sort. Here you give it the type. In our case, it's vk physical device. Queue family properties. The items would be, well, our queue family properties stuff. And the context is, well, as Travis said, a literal that guy. And here it seems like we need a lambda kind of thing, which would take a context. Likely not there because it was a very recent change. Yeah, well, we'll see. So here, less than function. Okay, let me just make sure I'm getting this right. So I'm just gonna copy this guy. Now we're gonna, I guess, do that trick where you basically say struct and you say dot lambda, and here you create that thing. You say fn lambda. Or honestly, instead of that, we would leave this job for the caller. So let me grab this guy. And would basically let the caller do it. Like give that. So you would basically have a selector, a sorter, and maybe you could even have a filter. But if you like the full pack. So yeah, we could even make the sorter basically what can I say, optional, right? So if there is no sorter, if the caller doesn't give a sorter, then it wouldn't sort. As simple as that, I guess. So I guess I would say, let's see, maybe sorter. Okay. And it would be, this guy, I think. No? Okay, let me grab this signature. Now, honestly, let's not overcomplicate things real quick. Let's just do it inline for now until we figure this how this works. Honestly, I'm getting ahead of myself here. Key families properties, and then type of context. Well, I think type of context here is void, or what exactly? Or I could just simply say type of that. No, this in parameter name. Huh. Oh, how would this work? Oh, never mind. What? Yeah, type of, I guess, this. Does that make sense? I mean, you would have a context maybe is equal to this basically, and we could basically say context. We would pass it here maybe, and then we could say context type of, well, context. Simple as that. But the thing is, we have to call this something else now. I don't know what to call it. Let's say CTX maybe. That's left hand side and right hand side. In this case, it's basically VKQ family properties. That's the T. Right? Okay, for now let's just return true just to see if this even works, even compiles or not. Okay, I think, but of course before that we should actually, oh no, it's fine. Okay, all right, let's see Zig build run, see if this works by any chance. I mean, it seems like it works. I mean, it compiles. So struct less than. Okay, I'd like to actually figure out what. Okay, let's try to okay, I'm going to go through all the Q family properties so we can see what's going on right there, what's happening. Q family properties, and let's just debug print that, and then we would say Q family properties, and let's see what's going on right there. Okay, and again I forgot that tuple thing. Let me just disable this guy for now. Let's just go with validation layer. Okay, I need the new line. New line. Clear, Zig build run. Yo, why is this crazy? Well, that's so bad. Let's just say, let's choose something. For example, Q count. Okay, cool. Zig build run. And there you go. So in this one, it's basically saying 1, 2, 8, 16. Yeah, so it's reversing it in this case. If I say false, it would keep it like it is. Okay. Yep, that's exactly the case. 16 to 8, 1. Yep. So if you say false, if you return false, it would not flip the positions. If you say true, that means it would flip the positions. Okay, let's see. So RHS, I guess. Let's try to start with Q count, for example. So RHS Q count greater than, let's say, well, actually let's start by LHS. So it's Q count. Let's say maybe, for example, less than RHS dot Q count. Let's try this one. So as you can see, it's sorted by 1. So from, yeah, so basically here, kind of like saying the first element should be less than the second element, kind of in terms of Q count, of course. Nice. And also, what else? Let's see. And also, now that's a good first step. And yeah, I think that's pretty much it, isn't it? Oh yeah, I wanted to actually basically see how much bit flags in the thing. Okay, cool. So how we're gonna do this? Well, let's figure this out. For now, I'm just gonna put this into a comment for now. And let's try this out. So Q flags. Okay, so how would I get how much flags I have? Okay, here's the deal. I'm going to do something similar, I guess, to what I've done with the C code when I actually implemented this in C, I remember, or even in Rust, I guess. But anyway, so to int, I would make this into an integer. And I need to find out some way to count how much SID bits are in that integer. I wonder if there's like some kind of thing for it. Well, I wonder how you would do that in Zig. Count SID bits. So in Rust it was, I believe, count ones or something. Yeah, exactly. They count ones. Where's the documentation for that? Yep, exactly, this function. This is the function that I actually used in Rust, I remember. So you'd basically give it some kind of number, and it would look for the binary representation, and it would give you how much SID bits there is. So in this case, there is 3 SID bits. Now, Zig has CTZ and CLZ. Ooh, let's see if that's the one. Can I find it? Hold on. Where's the documentation? There you go, CLZ. Oops, wrong one. Yeah. I think it's pop count. Let's see. What is it called? Pop count. Let's see. Exactly, yeah. Exactly, number of bits set in an integer. So that's how we could do it. If operand is a count time known integer, the return type is count time ends, otherwise, okay. I think this is the one, right? So pop count, let's see. So basically, pop count. I don't know why they named that though. Weird. So anyway, let's see if that works. But of course, let's say for example less than RHS flags.toInt. Yep, 28116. Population count. I guess I agree, kind of fun and funny. Oh yeah. Well, now how would I actually do the both? So it should queue count be the case, and also that guy, the queue flags. So let's try to think about it logically. I guess you would say that or that, I guess. So I think you would basically say this or this. Maybe. Let's see how that goes. And we got 1, 2, 8, 16. Now, since we're linearly going through it, it would check the most specialized. It would check it. It would try to select the most specialized first. That's basically the logic behind this. Hopefully, so yeah. So I think they should. This is basically what we were trying to do, which is honestly very interesting. So 1, 2, 8, 16. So I think that's pretty much it, right? Okay. Lovely. Let's try maybe to go with maybe queue flags, for example, and see what's going on with that one. Oh man, that's crazy. But basically, Okay, so the video decode bit is the first one. But anyway, so this is, I guess, this is the thing that we wanted. Now let's see which index is being chosen or selected. CTB debug print, let's go. Q family. So now it should hopefully select the third one. Did I just, let's see, caps viewer. So hopefully right now, I guess it would select this guy. The Q family 2, because it have compute bit and it's probably the least Qs it has. So anyway, all right, let's see if this, how this goes. Okay, index 2, which means the third key family. Let's go. We have done it. So now we're selecting that guy. Cool, amazing, perfect. Let's go. Next thing would be to basically, because when you create the device, you create with it the queues that you're going to use for the device. So right now, I guess maybe we could make use of a struct queue, kind of. Although we don't really need it right now. But there's not a lot of time left, I think. So we're just kind of trying to do something very quick. Okay. So const queue equals struct. Okay. So this every queue would store the device, and it would store, I guess, the D. Let's see. So the, well, what I'm doing, device, and then it would store the handle, which is going to be a vk.queue. I don't think allocation callbacks is needed there. So anyway, fn init. And I don't think this can fail. It would just give you back a queue. And fn dinit void. I don't think you need dinit though. Yeah, you don't need that. Okay, so you'd basically pass in the device. And you'd also pass in the key family index. Or you could just call it key family, but honestly, there's no need. Just say key family index. It would be, I guess, U size for now, or U32. I don't know what to use there, but anyway. And or honestly, maybe we could still go with the Q family. Anyway, never mind. For now, this is fine, I guess. Anyway, if there's something that suggests us to change that, we'll do it. But for now, this is fine. And of course, I do need another function in the device dispatch. We would say .get queue, get device queue. And of course, again, make sure that autocomplete wouldn't make jokes on you by letting you do this one. It happened to me once, I think. But anyway, get device queue to, not queue, not to, but anyway, true. And get device queue, let's say, let's go. So here it would say, I think it would return this, a new struct, and it would say, device, first of all, that's simple, device. And then finally .handle, I guess, is equal to device.vkd.getQueue, get device queue. Although here we're honestly opening the door. Anyway, never mind. Device key family index. Let's go. Well, honestly, you could probably infer that it is for the queue, so let's just say family index there. I mean, from the context, so you're creating the queue, so it's obvious that the family index is for the queue. So okay, and then finally the index of the queue itself, because you could basically request multiple queues out of the same family, because, well, so anyway, family index is going to be, well, also usize maybe. But of course, this is expecting, so I'm going to say int cast u32 family index and int cast u32 q index. Oh, I see. Of course, this can't fail. It would just give you the queue directly, so that's pretty much it. And is there something other than that we're wrong here? Index. No need for queue there. Let's go. Can I do this? Yeah, pretty much. Seems like. So terminal, zig build run. Seems to be all good, but well, we still didn't use that. So right now we could basically get the queue. So const queue is equal to device, well, queue, so init, give it the device, and then you would get the queues that you have requested. Although you probably, if we'd like to enforce a bit of error handling, like there's no need for error handling there, like basically enforcing correct behavior, we would probably, when we're creating the device, we would do that stuff, I guess. But anyway, for now this is fine. So family index, it would be, well, the chosen one, the chosen family, and then it would basically, yeah, no, index, right? And then here you would just say 0 in this case. Well, we only have one queue, and it's going to be the first queue, so index 0. And yeah, pretty much. Oh yeah, device.handle. Yo, what all this stuff I'm printing right now? Oh, because the queue. Well, I guess I'll just go with the handle. And there you go, vacate queue. And it seems to be giving us the actual queue there. Nice, 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 nice. So there is this way, or we could also do it here in the init function, maybe of the device. So you could basically give a collection of queues here. So basically something like, instead of self here, you could say I guess queue. So a slice of queues. Now we don't even need to return device 2 because queue already keeps track of its own device. You know, so So you could basically take any queue you'd like and just get the device from it. So yeah. So now what we do basically is so here, this is your device, const device stuff. So const device is equal to that. But of course here we're gonna say vacate dot device. Let's go. Shadows local oh, I see. Well, let's just call it dev for now. And I guess let's call this handle actually. Void handle. Now I guess I could use that device thing. Right? And then I would return for now well, aren't we getting a queue family here? I mean, we're supposed to later on be able to like return multiple queues, but for now this is fine. Queue family dot index or what? Yeah, the index here and here's 0. Yep, pretty much. So yeah. Now what's happening here is that you're gonna get the queues here. Okay, and you can say that, and then you could get one queue out of them. So for example, you can get this, the first queue in this case, and then you could say defer queue.device.dinit, or you could basically say const device, and you could extract it from one of the queues. And yeah. Now, why this design would be better is because the device is where you actually request queues. So with this kind of way, we're making sure to have the device is responsible for requesting the queues, and at the same time to giving us the actual queues that requested, instead of having to tell the device to request the queues and then manually us, the caller, we're responsible to making sure that we're getting the queues that we have requested from the device. So yeah, basically kind of like the design that makes sure that you're doing the right thing, kind of thing. So, but let me know if there is a better way. Anyway, so that's what I'm doing here. Sig build run. Type vacate.device does not support structure initialization syntax. Oh, device, not vacate device. So all right, time's up, but I could basically say const queue right now. Sig build run. Okay, done. We're done with it. All right, so that's it. I'm gonna end this stream right here, and of course I'm going to publish this repo later on. But yeah, see you later, guys. Goodbye. Goodbye, everyone.